I mean, one has to look more careful, but I'm a bit suspicious. Thank you. It's okay. Not a huge problem.
So we have one more announcement before the next talk. So actually, after the next talk, we are going to take a conference photo before the coffee break. So please stay alert. There will be more, somebody will guide you where to go and how it's going to be taken. It's just going to be outside, but like please follow somebody with the camera. Thanks.
Okay, I think we're ready to proceed. So our next speaker is Fiona Seibold from EPFL, and she will tell us about integrable deformations of ADS3 strings. So please, Fiona.
Thank you very much, and thank you to the organizers for giving me the opportunity to speak at this wonderful conference. So in this talk, we will embark on an exploration of the landscape of integrable deformations of ADS3 strings. And let's start by giving you some motivation why constructing and studying this type of integrable deformation is interesting. One of the motivation comes from the celebrated ADS-CFT correspondence that we have already seen in previous talks, especially the duality between the type 2b superstring theory on ADS5 cross S5, which is dual to n equal 4 super-Young-Mills in flat dimension. And as was also already mentioned, it's some specific limit, namely the one where the strings are free, which corresponds equivalently to the planar limit in the gauge theory. These two sides of the duality actually become integrable models. So this is very interesting because the integrability machinery can then be applied in order to obtain exact results, so non-perturbative results, which allow to test the duality at any value of the 't Hooft coupling. And this then begs the question whether there are other theories, especially superstring theories, to which this powerful integrability techniques can be applied in order to learn new lessons about quantum gravity and holography. The answer, of course, is positive, and there are different ways to approach that question. So one direction is to look at integrable theories or holographic setups in the lower dimensions. So for instance, when the strings propagate on some background containing an ADS4 or ADS3 or ADS2 factor, and some of these string theories will still be integrable. And the lower you go in dimension, the less supersymmetries the theory has. So you will have much less supersymmetries than what you have, for instance, in ADS5 cross S5. And this generates new interesting physics that is good to understand. And the fact that you have integrability then allows to have some handle on these new properties. Another direction that can be followed is through the construction of integrable deformations. So instead of jumping in dimension, here you will construct something that is continuously deform some known integrable theories. So you start from some known integrable theories and then continuously deform it in such a way as to preserve the integrability of the model. And in this talk, I will merge these two types of directions, and I will consider integrable deformations of ADS3 strings. So I will go in lower in dimension, considering ADS3, and construct integrable deformations. Now, to restrict a bit the space of integrable deformations, that is pretty large, so we have seen in the previous talk these TT-bar deformations. I will be more interested in deformations that deform the space-time geometry in which the strings propagate, but there will be some connections, as I will highlight. And so this landscape is very broad, and in order to be able to restrict it a bit, I will consider supersymmetric integrable deformations. So the integrable deformations will break some of the supersymmetries, but some of them will be retained, and throughout this talk, this will actually be half of the symmetries will always be there, so half of the original theory here. And these results that will be presented are mainly based on work that I did with fantastic collaborators. So Ben Hoare, Anna Rettore, Alessandro Sfondrini, and Arkady Zeitlin, and the two last ones are in the room. The plan of the talk is as follows. I will just start with some very, very brief review on the status of integrable ADS3 strings. I think we will hear more about this program today and tomorrow. Then I will present what is perhaps the simplest type of integrable deformation that one can construct, namely TST transformations. I will then crank up a bit in difficulty and present trigonometric and elliptic deformations. So these are really newly constructed deformations that I want to present. And throughout this exploration, we will encounter the question, so how to test whether the theories that are constructed are actually integrable, and also both at the classical level and at the quantum level. And in order to answer that question, I will need to introduce the so-called worldsheet S matrix, and I will then see what this worldsheet S matrix, the form it takes for these different types of deformations. Finally, I will finish with some conclusions and give an outlook of open problems that still need to be addressed, and there are many. So let's start. Oops, sorry. Okay. Let's start with the ADS3 strings background. It will be the starting point of my integrable deformations. So there are three solutions to the type 2b supergravity equations of motion that have this ADS3 factor and that preserve 16 real supercharges. So these are the three backgrounds mentioned here: ADS3 S3T4, ADS3 S3K3, and ADS3 S3 S3 S1. There is a huge literature on this string theories. What will be interesting during the talk is that these theories have a superisometry algebra that have the symmetries factorized into two copies. So for instance, in the two first cases, these two theories present two copies of the PSU1,1/2 superalgebra, in which in each copy there will be 8 supercharges. And similarly for the third case, the geometry presents two copies of the D21 alpha superalgebra. So this parameter alpha in the D21 alpha, it controls the ratio between the three spheres that appear, the ratio of the radii of the three spheres that appear in the geometry. And by sending this parameter to 0 or 1, the S3, S1 geometry decompactifies into a T4. So there is a way to go from this geometry to this one. And similarly, it's also possible to do that at the level of the algebra. Another interesting factor is that these type of geometries have a lot of moduli that one can play with. In particular, they can be supported by different combination of fluxes. There is the pure NS geometry, there is the pure Ramond, it can be supported by pure Ramond fluxes, or also a mixture of both. So this is a difference with respect to, for instance, the ADS5 cross S5 superstring. And importantly for this talk, all of these three cases are integrable, at least in the limit of free strings. So this has been rigorously proven for classical integrability for ADS3 S3T4 and ADS3 S3 S3 S1, including by people at Nordita. And it is believed that the integrability will also hold when replacing the T4 with K3. So these are integrable theories, string theories, and they will serve as my starting point in order to deform the theories. So let's start with the simplest type of deformation that I want to introduce, these TST transformations. So these TST transformations, you might already have encountered them, and they are interesting because they can be applied whenever the background geometry that you are investigating or working with presents two U1 isometries. And here I will assume that these two U1 isometries are realized as shifts into coordinates phi1 and phi2. So this TST transformation, as the name suggests, can be decomposed into 3 steps. The first step consists in doing a T-duality in one of these coordinates, phi1. It goes in some T-dual coordinate phi1 tilde, and that at the level of supergravity, for instance, if starting from a type 2b background, this will map to a type 2a background. Then in this T-dual theory, you perform a shift involving the other coordinate phi2, a shift parameter beta, real, and this T-dual coordinate phi1 tilde, and then you T-dualize back in order to land again on a solution of the type 2b supergravity equations of motion. So some properties that make this type of deformation interesting. So first of all, it maps string backgrounds to string backgrounds. So you are always guaranteed while performing this type of transformation that you will land on a consistent string theory. And it's relatively easy to implement it at the level of the background because there are these rules, these Busher rules that really tell you how the metric, B field, and flux is transformed. Another interesting property of this type of transformation is that it often has a clear interpretation in the context of holography. So this is true, especially if the TST is realized not, of course, on the ADS factor to preserve conformality, but in the compact space. So for instance, I would say the canonical example of this is the duality between the Lunin-Maldacena background, which is a deformation of ADS5 cross S5, where the TST is performed along the two U1s inside the S5, which is dual to the Lie-Strasser deformation of n equal 4 super Young-Mills, which is still conformal, but preserves only n equal 1 supersymmetry. So these type of deformations have been, so for instance, for this example, they have been mostly looked at from the point of view of ADS5 cross S5. And there is some literature also for ADS3, but it's still in progress. And here I would like to show you some recent results. So I will start, the starting point will be where is the, okay. The starting point will be the ADS3, S3, S3, S1 background that I will focus on the pure Ramon case. In fact, throughout the talk, I will only consider the pure Ramon setup and construct deformation of this theory. So there are 4 different factors. ADS3, there are the 2 3 spheres, and there is the S1. And inside each factor, there are several U1s that one can play with. And they can be decomposed into the U1s that belong to the left D21 alpha and the U1 that belong to the right D21 alpha. And there is a similar decomposition for the 2 3 spheres. So the type of TST transformations that I want to construct. So first of all, I want to preserve the ADS3 background so that ultimately I want to be able to consider them in the context of holography. So I will not touch these 2 U1s. And then on top, I want to preserve half of the supersymmetries. So here I choose to only deform the right copy. So I will only consider these 3 U1s. So the U1 right inside the 2 3 sphere and the U1 of the S1 factor. So there are 3 U1s that I can play with in order to construct this TST transformation. So in principle, I could construct a 3-parameter deformation in that case. But this obscures a bit the geometry. And in order to convey the main message, I will focus on 1-parameter deformations. So I will consider the TST transformation in these 2 U1s and also the TST transformation in these 2 U1s. So let's start with the TST involving a U1 of the 3 sphere and the U1 of S1. In that case, the geometry, so again, it's the way you can implement this TST transformation is through these Busher rules. And what to obtain is that the geometry, the sphere that is involved in the T-duality becomes squashed. So the metric takes the following form, where you have a base manifold that is S2, and then the fiber A, and then you have some squashing parameter delta in front of the fiber. And this squashing parameter is related to the TST transformation beta through this relation. So if you want to preserve reality, so beta is real, delta is between 0 and 1. This is why I call this a squashing. So this is for the metric, but of course one also needs to consider the whole geometry. So here I will give you also the dilaton of the fluxes. What is interesting is that the dilaton remains a constant. So we have seen in previous talks other cases where there is this type of warping factor, but this warping factor was depending on a dynamical coordinate. It wasn't a constant, and therefore there was also a non-trivial dilaton. But here this dilaton really remains constant. Another important feature is that while we started with pure Ramond background, this TST transformation generates an NS flux, and the 5-form flux is also turned on. So here delta equal to 1 corresponds to the undeformed theory, where the geometry is just supported by the 3-form flux, where here omega represents the volume form of the different factors. An interesting limit is to consider the strong deformation limit. So when the parameter in the TST transformation goes to infinity, and in these parameters, this corresponds to sending this squashing parameter delta to 0. Now, in order to make sure that this limit is well defined and there is no the degeneracy in the metric, one also needs to do a rescaling of the coordinate in the fiber. But when doing that, the metric and the background fluxes remain finite, and there is a flat direction that appears, but all the fluxes remain turned on. And this, in fact, if you stare at it for a long time, or for a short time, this will give for you the ADS3, S3, S2, T2 background, which, as was shown in that paper, which actually gives the classification of backgrounds that are classically integrable and have an ADS3 factor. Well, this background was already found in that paper. Perhaps a slight remark is that here I wrote T2, but from this construction, of course, you cannot really distinguish between T2 and R2. So the conclusion is that starting from the ADS3, S3, S3, S1 background, doing this TST transformation represented by this line of series in this blue line, taking some limit, one can reach the ADS3, S3, S2, T2 background, which is another type of another classically integrable background, but with less symmetries. Here I put also an arrow going from that background to that one, but of course, because it involves this scaling limit, you cannot do that using in a straightforward way. Now, so let me just schematically tell you what happens when doing the TST transformation in the 2 U1s of each 3 spheres. In that case, you again get a squashing geometry, and the 2 3 spheres are squashed with the same squashing parameter delta, and this allows you to construct a deformation, a family of series that then interpolates to ADS3, S2, T2, ADS3, S2, S2, T3, which is another classically integrable background. You can also take this limit where alpha goes to 0 and 1 to land on the ADS3, S3, T4 background, and similarly to the TST there in order to land on yet another classically integrable background, ADS3, S2, T5. So what are some properties of these blue lines, so these interpolating backgrounds that are interesting? So first of all, they preserve the ADS3 factor, which makes them interesting to study in the context of holography. They also preserve, so throughout, for all this family of theories, they preserve the classical integrability of the theory. So in principle, all the integrability machinery can be applied to them. This is particularly interesting because these 3 theories have actually been much less understood from the point of view of integrability, and being able to construct integrable backgrounds where you can really follow what happens to the integrability techniques all the way down and take the limit, perhaps it will help us understand these backgrounds better. And throughout the flow, or throughout this deformation, you preserve 8 supersymmetries. And so these 8 supersymmetries come from the copy of PSU1,1/2 or D21 alpha that remains undeformed while doing the transformation. So this was one type of deformation that one can construct. Let me also just give you some comments. So first of all, here I only deformed the compact directions. It's also possible to deform the ADS3 factor because of the different signature. There will be the possibility to have time-like, space-like, and null deformations. Another comment is that by doing this deformation of ADS3, one can land on backgrounds containing an ADS2 geometry, which could also be interesting to be studied in the context of holography. Another comment is that these TST transformations are just special cases of a broader class of deformations that are called homogeneous Yang-Baxter deformations. This type of transformations, they really change the geometry and may break all of the supersymmetries, but what is important is that strings propagate, so strings with periodic boundary conditions propagating in these deformed backgrounds can equivalently be seen as strings propagating in the undeformed geometry but having twisted boundary conditions. So in some sense, this deformation changed the geometry globally, but not locally. So now I want to introduce other types of deformations that will really change the geometry locally as well. So these are these trigonometric and elliptic deformations. So the trigonometric deformation, it can be traced back to the work of Cherednik, who looked at the deformation of the principal chiral model on SU2, and this corresponds to having a string propagating on a 3-sphere. And this trigonometric deformation, again, gives this squash geometry of the 3-sphere. So here I just wrote it in some other way that is more convenient later on when I will discuss also elliptic deformation, but this E1, E2, E3 are the undeformed film bind of the 3-sphere, and then there is the squashing parameter beta appearing here. However, contrary to the TST transformation, in that case, it is not supported by any B-field. So my geometries here will not have any NS flux, and this will make a big difference. One of the differences is that, so this geometry, so this principal chiral model has a left-acting SU2 and the right-acting SU2, similarly to what we have seen before. And this deformation breaks the right-acting SU2. However, there is actually a hidden symmetry. So this is a quantum group symmetry. And the way you can think of this quantum group symmetry is really, so this is really a deformation of the universal enveloping algebra, but naively you can just think of it as taking your generators of SU2, J3, J plus and minus, and then deform the commutator between the positive and negative root. Instead of giving a J3, this will give some Q deformation of J3. So this parameter Q is some real parameters that is related to the deformation parameter in the metric. So contrary to TST transformations, this really deforms the geometry locally. So you cannot really think of them as being strings with twisted boundary conditions. This trigonometric deformation or these quantum deformations, it is known how to generalize them to cosets. So for instance, to consider quantum deformation of S5 or ADS5, and also to super cosets, so how to deform superstrings. In particular, this can be used to construct deformations of ADS3, S3, T4 or ADS3, S3, S3, S1. The case of K3 is a bit more tricky. These deformations, they will preserve, again, H supersymmetries as long as the deformation is only done in one copy of the superisometry algebra. Now, a subtlety is that for TST transformation, it was always guaranteed that starting from a string background, you will land on a string background. Here, while doing this, so this deformation initially was really studied from the point of view of integrability, so it will preserve integrability, but the interpretation in string theory is a bit more tricky. And in fact, one can have different quantum deformations that are classified according to the Dynkin diagram of the superisometry algebra. So for instance, for PSU1,1/2, there are 3 different thinking diagrams. So here the node with a cross represents a fermionic root, and the node here represents a bosonic simple root. There are some fermionic dualities that allow to go from one thinking diagram to the other. But what is interesting is that the interpretation of this deformation in the context of string theory is not equivalent for all thinking diagrams, and in fact only this fully fermionic thinking diagram leads to a supergravity background, so that you can interpret the deformation as some deformation of the string theory. So now elliptic deformations, they introduce an additional deformation parameter. So before, there was still a U1 rotating the 2 field bind E1 and E2, but here this is further broken down. And in fact, the whole right-acting symmetry is broken. Now, this type of deformation, so here written down for the 3-sphere, it can be generalized for non-compact groups, in particular to ADS3, but it's not known yet how to generalize them to coset models. So we don't know how to do an elliptic deformation of S5 or ADS5 cross S5, and we also don't know how to generalize them to supercosets, so how to do integrable deformation of superstrings in a systematic way. However, what we managed to do recently is to embed this deformed background, this elliptic deformation of ADS3, S3, and just having some flat T4 directions into supergravity, so into type 2b supergravity. So this turns out to be possible. And let me just sketch how the background looks like. So it has a trivial dilaton, as for the TST transformation. So here, for convenience, I will set it to 0. It doesn't have any NS flux. This is what I try to highlight, what is the difference with respect to the TST transformation. There is, again, the 3-form and the 5-form flux that are turned on, and these are actually given by linear combinations of 4 auxiliary self-dual and orthogonal 3 forms. So here, F3, 4, you recognize the volume form and ADS3 and S3, but the other 3, they really mix the ADS3 and the S3 sectors in a non-trivial way. And these X1, X2, X3, X4 are 4 vectors of 4 components that parameterize the deformation. Those are the deformation parameters in the Ramon-Ramon fluxes. The J2s are the self-dual orthogonal 2 forms on the torus. So, of course, there will be some constraints on these deformation parameters. So supergravity imposes constraints on the norm and the scalar product of these vectors of deformations. So this restricts them to just 10 parameters in the Ramon-Ramon fluxes, and also requiring that the background preserves 8 supersymmetries, then also restricts these further. So this is actually equivalent to the statement that the vectors of parameters lie in a 2-plane. And we also checked that the killing vectors and the killing spinors of this geometry generate the PSU1, one copy of the PSU1,1/2 superalgebra. So the bosonic model was constructed using this Cherednik elliptic deformation, and it's known that this preserves the integrability of the model. And we also managed to embed this integrable bosonic theory into supergravity, but what about the supersymmetry? So is it an integrable theory, what we just constructed? And in order to address that question, I need to introduce for you the concept of worldsheet S matrix, which will really allow us to test the integrability of the model. So this is a picture of the integrability program applied to the string sigma model. So the string sigma model has a lot of redundancies. So there is some reparametrization invariance. There is also some symmetry, kappa symmetry for the fermions. And the first step is to gauge these symmetries away. And this is done through what is called the Lycon gauge fixing that we also have briefly encountered in the previous talk. this then defines a theory on the cylinder. So here I consider closed strings. So this is the world sheet of the closed strings. And then the additional step consists in taking the decompactification limit, where now this decompactifies into the plane. On that plane, you have a well-defined two-dimensional quantum field theory, for which you can define asymptotic states. The S matrix can be computed. And integrability then imposes restrictions on this S matrix that we have also seen in the previous talk. In particular, there cannot be any particle production, and a n-body scattering event factorizes into two-body scattering processes. And this imposes some constraints on the two-body S matrix, which is the celebrated Yang-Baxter equation that was also mentioned. So in order to test whether the model is integrable, one way to do that is to follow this route, compute the S matrix, and check that the Yang-Baxter equation is indeed satisfied. So I will not go through the details of this Lycon gauge fixing. However, I will mention that for the ADS3S3T4 case, doing this procedure then gives you a non-relativistic theory for 4 massive bosons, 4 massive fermions, and also 4 massless bosons and 4 massless fermions that come from the T4 directions. The S matrix, of course, you can compute it using perturbative calculations, but really the power of integrability is that in that case, you can bootstrap it using symmetries. So here, I wrote down the bootstrap equation for the S matrix. And again, there are some caveats. So this only fixes the S matrix up to dressing factors that still need to be fixed using more physical input. And this program has been followed with great success for the undeformed ADS3S3T4 and also ADS3S3S1 case. Now, what happens for the deformed theories? So one first comment is that in these deformed theories, sometimes you break the symmetries that are usually used for the Lycon gauge fixing. So one needs to consider alternative Lycon gauge fixings, and different choices of these Lycon coordinates that enter the Lycon gauge fixing, they actually lead at the level of the Lycon gauge fix theory to TT bar deformation that we have just seen, but also more general current deformations. Especially, and a corollary of that, if you want, is that if you do a TST transformation in the 2 directions that are used for the Lycon gauge fixing, this actually corresponds to performing a TT bar deformation at the level of the Lycon gauge fix theory. So this is when the TST is performed in these coordinates that are used for the Lycon gauge fixing, but you can also do the TST just in the transverse coordinates that are not affected by this Lycon gauge fixing. And in that case, the S matrix gets dressed by a Drinfeld twist, and this Drinfeld twist satisfies some co-cycle condition, which really ensures that if you start from an S matrix that satisfies the Yang-Baxter equation, this dressed S matrix again satisfies the Yang-Baxter equation. So integrability is preserved as it should. For trigonometric deformation, this is not possible, so you cannot do this twisting, again, because the geometry is changed locally, but you can use this hidden quantum group symmetry in order to, again, bootstrap the S matrix. So remarkably, this quantum group symmetry is still powerful enough in order to bootstrap the S matrix, and this has also been done for ADS3S3T4. However, for elliptic deformations, the symmetries and the exact S matrix are not yet known. So we don't know what the symmetries are. We don't know what the generalization of this quantum group symmetry, which would be some type of elliptic symmetry, would be. So, however, we can make progress by just considering perturbative calculations, just as in standard quantum field theory. And we will restrict to the massive sector because I told you there are some massless bosons, massless fermions that appear, and these, in perturbation theory, they are problematic because they involve some IR divergences. So here, in order to be safe, we will just focus on the massive sector. So the Lycon gauge fix theory can be expanded in inverse of the string tension, and similarly then the S matrix has some, is the identity plus the first interactions plus high loop corrections. So what we did is to compute this tree-level S matrix using the background that we suggested, and we found that it satisfies the classical Yang-Baxter equation, which is a strong indication that the model is actually integrable. So that's very good news. The S matrix that we find has a completely new form with respect to undeformed ADS3, S3, T4. It's reminiscent of an 8-vertex model, but it falls outside of the different classifications that have been done so far. In a limit, it also goes to the tree-level S matrix on ADS2 cross S2, so it provides some interpolating S matrix, which is again interesting because these geometries are also not well understood from the point of view of integrability. So let me now come to the conclusions and an outlook. So conclusions is that there is a very rich space of integrable deformations of ADS3 strings. Some of these deformations preserve 8 supersymmetries. Some interpolate between known integrable backgrounds. We also constructed a new type of elliptic deformation of the ADS3 S3T4 superstring. And we checked that the tree-level S matrix is compatible with integrability. It presents some new interesting features, so it would be very interesting to build on that work and to actually try to find some exact S matrix that represents this type of integrable scattering. So what are some open questions? So as I just said, so it would be very interesting to find the symmetries in this elliptic deformation to be able to construct an exact S matrix. It would also be interesting to understand the relation between these two other types of S matrices of 8-vertex type that were constructed by just bootstrapping the Yang-Baxter equation. Because I said it falls outside of this category, this classification, so whether this classification can be generalized. What is the relation to other types of integrable interpolating S matrices that have been recently proposed? Also here I really told you how to obtain the S matrix for these integrable, these deformed theories, but obtaining the S matrix is really the first starting point to apply the integrability program. So we still need to understand the beta ansatz, the thermodynamic beta ansatz, or even find a quantum spectral curve for this deformed ADS3. So this is something that even is under progress for the undeformed case. So first one is to fix that. Another question is that there, in the literature, one can find many other families of supersymmetric backgrounds that have this warped ADS3 or S3 geometry. And so what is the status of integrability in these theories? Are they somehow related to the ones that are constructed through TST transformation or these trigonometric deformations? That would be interesting. Another one is how to lift this type of deformation to the brane setup. And of course, the bigger question is how to interpret the type of deformations in the context of holography. Thank you very much for the attention.
Thank you very much for the nice talk. Other questions?
Thank you. Thanks for the talk. Could you comment, please, a bit more on integrable deformations for warped ADS cross-S geometries and potentially the holographic interpretation?
Okay, so in the literature, using compactifications, there have been geometries that were proposed that also have this warped ADS3 geometry of also null or time-like or space-like warping, and also deformed S3 geometry, and they also obtained some fluxes. But this was obtained from, I would say, a supergravity perspective, and whether these models are integrable or not, this has not been explored. So this is what I was meaning here in terms of what would be interesting. The other point about the interpretation in holography. So I mentioned that for ADS5 cross S5, at least in one specific case, we have a good handle on what these TST transformations, for instance, do at the level of the duality. We know exactly what the dual CFT is. So what happens for these deformed theories? This is what this open question is. So in the case of ADS5 cross S5, where well, first of all, in the undeformed theory, the dual is known. It's n equal 4 Young-Mills. There has been some progress for these like homogeneous Yang-Baxter deformation or TST transformations, and this corresponds to more general non-commutative geometry. However, for ADS3, even the undeformed case is still explored, especially what happens in the case of Ramon-Ramon fluxes, which is really the setup that I chose in that talk. And in that case, very little is known about the interpretation in holography.
And what do you expect what do you expect the holographic interpretation to be in the warped case in this?
Okay, so you probably mean in the warped ADS3 case, right? Yeah, so this will, so in that case, you will no longer have a CFT, or at least you will no longer have a CFT2, but because you still preserve one copy of the SL2R, in some sense, there is a one-dimensional CFT sitting in there, so there will be also some interesting results in that sense.
Thank you very much.
Do you know what happens with Drinfield's twist in this limit delta goes to 0?
In which twist?
Drinfield.
In the Drinfeld twist when delta goes...
In TST deformed case, when you take delta to 0, do you know what happens with the Drinfeld twist?
No, I don't know, because there is a whole chain of calculations that one would need to do. So first you would need to understand the Drinfeld twist starting for this ADS3, S3, S3, S1, and then take the limit. So I don't know, but it should, it can be worked out.
Thanks for the nice talk. In ADS3 backgrounds, we expect not only the PSU or D algebras, but a full superconformal algebra, right? Either because logic being either there's a CFT dual, CFT2 dual, or because of the Brown and No construction in supergravity. Is any of this infinite dimensional algebra seen in these constructions? And I mean, so in NSNS background, for instance, this Givon, Kutasov, Seiberg, that constructed these charges. What happens to that under these transformations? Do they stay invariant, or do they transform into a new set of charges?
So I am not sure, but of course, because these theories are integrable, they also have this hidden Yang-Yang symmetry, so there perhaps is some relation to that. And this Yang-Yang symmetry, in the case of the trigonometric deformation, this is really what becomes the affine quantum group. So this is, you can also trace back in these type of theories what happens to these higher charges.
I see. And how does it transform under your TST or these transforms you're doing?
So for the TST, what happens is that there is you get a twisted algebra in some sense. But yeah, I cannot answer specifically because I'm not very familiar, but I can try to make the link with what happens in integrability.
Talk more later. Thanks.
If there are no more questions, then let's thank the speaker again. And do not forget the photo.
So it's picture time. So if you just follow Olga, then you'll be there. And you'll be on the photo. So you're
Very much. So I want to, well, first of all, thank the organizers for the kind of invitation to speak here. It's a pleasure to be in Audita. So I want to talk about this work in progress, but hopefully to appear very soon, probably next week, with my collaborators Vincent Caudrelier, Derek Haaland, and Anup Singh. So where we derive some variational formulation of the Hitchin system, so I'll explain the subtleties in that statement. And to start off, I want to first give some motivation for this work and for this talk. So it's in the context of this general correspondence, which was initially formulated by Costello and further elaborated by Costello, Witten, and Yamazaki, between integrable field theories on d-dimensional spacetimes, called M, and gauge theories in two extra dimensions living on the product of the manifold M and a Riemann surface C, which are holomorphic along C and topological, a mixture of topological and holomorphic along M. So the heuristic motivation for this correspondence is basically that underlying integrable field theories, you have a lax connection, which is a connection that depends meromorphically on a complex parameter. And so what the gauge theory does is it incorporates this complex parameter as part of the geometry. This is why you have this extra factor of the Riemann surface. And the idea is that the gauge field of the gauge theory becomes this lax matrix, which is inherent to integrable field theories. So there's been a lot of examples of this general picture in various dimensions. So the first one was this 4D Chern-Simons one on a two-dimensional space-time product with a Riemann surface. And this corresponds to two-dimensional integrable field theories on the two-dimensional spacetime. So I should say that, well, this was first of all initially developed by Costello and Yamazaki, and then later by lots of people. And it's really mostly been understood in the context of the Riemann sphere and also elliptic curves. So we've seen in the previous talk some examples of elliptic integrable models, and they fall in this category. So these are 2D integrable field theories, so string theories fit in this column here. And because the world sheet is two-dimensional, and elliptic deformations are those where the Riemann surface is the elliptic curve. So there are also high generalizations, which I won't talk about at all today, but they are all mostly understood in the case of the Riemann sphere. We don't know much about high genus Riemann surfaces. And the point of today is I want to go down in dimensions to 3 dimensions, where there's this correspondence between what's called 3D mixed BF theory on R cross a Riemann surface and Hitchin system. And the reason I want to go down by 1 dimension is because the Hitchin system is a very beautiful and rich integrable system, which can be formulated on any Riemann surface of any genus G. So in particular, this correspondence, I will explain how it really works on any genus. The Hitchin system is an example of a completely integrable system. So there's a whole hierarchy of Hamiltonians part of this system. And so the aim of the game will be to describe a Lagrangian for this hierarchy of integrable systems. And the other thing is that we're able to actually derive a 3D mixed BF theory from considerations of the Hitchin system. So usually what's this story, what you do is you start with a gauge theory, you fix the gauge, and you end up with an integrable field theory. So what I'll show here is you can actually think carefully about the Hitchin system and realize that actually it's described by 3D BF theory. So you go the other way. Okay. So let me start by describing precisely what I mean by completely integrable system. So I am assuming not everyone here is familiar with this. So let's take an n-dimensional manifold. And if you consider the cotangent bundle and you have a Hamiltonian on this cotangent bundle, the dynamics induced by this Hamiltonian is called completely integrable or Liouville integrable if there are n functions on the phase space which have the following 3 properties. So they have to be conserved, meaning that their Poisson bracket with the Hamiltonian should be 0. The crucial property as well is that they are in involution, which means that they Poisson commute with each other. What this means is that the flow induced by any of these Hamiltonians, I call these Hamiltonians, they preserve all the other Hamiltonians. So in particular, what this tells you is that you can restrict with a constant level surface where you fix all these Hamiltonians to constants. So this describes a Liouville torus within the phase space, and the dynamics holds on these Liouville tori. So this is the notion of Liouville integrability. And crucially, we also ask that these are independent integrals of motion, of course, so that they're locally, their differentials are linearly independent. Okay, almost everywhere. So you can always find an obvious integral of motion if the Hamiltonian doesn't depend explicitly on time. The Hamiltonian itself is conserved because it Poisson commutes with itself. So H1 is usually taken to be the Hamiltonian, but the key point is that these second two properties, they are completely symmetric in HI. So they're not sensitive to any particular choice of HI. So in fact, all these other HIs, they equally define integrable systems on the same phase space. And so the integrals of motion of one system define also flows which are integrable in this precise sense on the same phase space. So it's very natural from the point of view of integrable systems to consider all these flows together. So we talk about the integrable hierarchy of the flows. Okay, so you think about all the systems together as one, and the key property is that these flows commute because of this involution property. Okay. So the question I want to ask today, because the title is about variational formulations, is how do you formulate this intrinsically Hamiltonian property that the Hamiltonians commute? How do you formulate it variationally? So this was answered in 2009 by a paper by Loeb and Nijhoff. So they introduced this notion of Lagrangian multiforms, which provides a variational criterion for integrability. So to motivate this story, let me start by just considering one Hamiltonian and remind you how you formulate that in a Lagrangian setting. So let's fix a particular I and look at the evolution of the phase space coordinates under this time Ti. So they're governed by these Hamiltonian equations for the Hamiltonian Hi. And these are encoded variationally in the first order Lagrangian given by PQ dot minus Hamiltonian. Okay. So really, this is a Lagrangian for a curve in phase space. So the curve is parameterized by the time Ti. And the action for this Lagrangian, if you vary it with respect to P and Q, you find the curves which are critical for this action. Okay. And crucially here, I insist that there's no sum over I. I'm really considering one time for the moment. So it's the Lagrangian Li times dTi. This is a one form which you can integrate over the real line. Okay, so the question is, how do you consider all of these independent systems together as one? How do you formulate a Lagrangian that encapsulates all of them? And crucially also, how do you ensure that the part of the dynamics is that the Hamiltonians Poisson commute? So you want this involutivity property to come out variationally as part of the dynamics. So the idea of Lagrangian one forms, which dates back to Loeb and Nijhoff and has been developed by many authors since then, is to introduce this notion of Lagrangian one form. So I'll be using a very recent reformulation of this language, which is due to Caudrelier and Harland, where they, for convenience, they introduced an extra copy of Rn, which is to treat the times on an equal footing to all the phase space coordinates. So this is just for convenience. You can do this without that extension, but it's nice to do it in this way. So in that case, you can write down a Lagrangian on this extended phase space where you have all the times as extra coordinates. And rather than thinking about individual curves in that space, because that would describe one particular system, you want to consider surfaces in that space, right? So you want to consider immersions of Rn, which are, Rn is this multi-time space parameterized by the different times. And you want to consider immersions of that into the target space. So you're describing a family of n different flows. And okay, so you take this Lagrangian one form on the T star m cross Rn. You can pull it back to Rn, so you get a one form on Rn, which is essentially what's in bracket here with the extra duj. That would be a one form on the Rn. But this is still a one form on the Rn, you can't integrate it, so you have to make a choice of curve, a smooth curve in Rn, so that you can pull back your one form on Rn to the curve and integrate that along the curve. So there's an extra choice of a curve to make. And the point is you get not just one action, but you get a family of actions for the degrees of freedom which are encapsulated in this function sigma. And the family of action is labeled by this curve gamma. Okay. So important to think that to realize that there are two functions involved. There's a curve gamma and there's this immersion sigma. These are on a very different footing. The curve is just an auxiliary curve probing this space of multi-times, whereas sigma is a function in the target space, in the phase space that encodes the dynamics of your variables with all these different times. Okay. So when you vary these actions, so you have to vary them for all values, or for all curves gamma. So you find the critical points with respect to sigma for all gamma. So that means you're varying with respect to p, q, and t. You get these equations here. And if you look at the last one, you notice, so varying with respect to t, you notice that if you substitute the first two into this equation, you basically get the involutivity property, except there's this Jacobian, so this matrix dti by duj, which you'd like to invert. Okay, so the key point is that this is possible because of the first two equations. If you look at the first two equations, if this matrix was not invertible, it would have a kernel, which would mean that dq mu by duj would also have a kernel, and so would dp mu by duj. And therefore, this differential of the immersion would not be injective. Okay, so that means that this matrix is in fact invertible by the assumption that the sigma is an immersion of an n-dimensional space into the cotangent bundle. So by inverting this dti by duj in every equation, first of all, we get the involutivity that we wanted, and we get the Hamiltonian equations for every single time ti in the hierarchy. Okay, so this is really a Lagrangian formalism encoding an integrable hierarchy. So all the times are described by the same Lagrangians, all the time evolutions, and it tells you also that the Hamiltonian is Poisson commute for free. Okay. And one thing that I want to do later in the Hitchin system is think about gauged Lagrangian one-forms. So this is a natural way of doing symplectic reduction in this Lagrangian framework. So let's think about having a Lie group G acting in a Hamiltonian way on the cotangent bundle with a moment map given by mu. And let me suppose that all the Hamiltonians are invariant under this symmetry, so that they Poisson commute with the components of the moment map. And then so what Hamiltonian reduction means is you restrict to the level set of the moment map equal to 0, and then you have to quotient by an extra residual gauge Lie symmetry G. So you go to this quotient, symplectic quotient mu inverse of 0 divided by G. So the point is you can implement this reduction in the Lagrangian framework very naturally. So first of all, you want to enforce the condition that mu equals 0, and this you can do by introducing a Lagrange multiplier. So because the moment map is valued in G star, the Lagrange multiplier should be valued in G so that you can pair it with the moment map. So you get this extra term. So you have the Lagrange multiplier A times the moment map. So this will enforce through the equations of motion for A the condition that mu equals 0. And I note here that this is a one form because I'm modifying a Lagrangian one form. Mu is a scalar function, so I need A to be a one form. So it's a one form field on Rn, the multi-times, valued in G. And then to pass to the quotient, what you have to do is just, you realize that once you've added this gauge field, or this one form field to the action, the global G symmetry gets promoted naturally to a gauge symmetry. So you can act with the gauge group of all smooth functions from Rn to G. You can act pointwise on the map sigma, so on the P's and Q's. And you let this one form field A transform as a gauge connection. Okay, so through this procedure, this one form field gets promoted to a gauge field along Rn. This will be very important to remember for later. So we have a connection along Rn from the process of gauging the one form. Okay. So you can derive the equations of motion in the same way as before. The new equation is just the variation with respect to the Lagrange multiplier, which, as we said, just gives you the constraint mu equals 0. The other equations are, of course, a bit modified, so they describe a constrained Hamiltonian system, where now the dynamics is not induced just by the Hamiltonian H itself, but also the Hamiltonian plus an arbitrary function of time times the constraint. So this is essentially implementing a gauge transformation along the flow at every instant in time. This A tilde is technically just the one form, but written in the coordinate t. Remember that in the previous ungauged setting, I had to invert the matrix dti by duj. I have to do it here as well, and this produces this new connection A tilde in the t coordinate. And the other nice thing is that if the action of G is is free, then these A's here actually describe a flat connection on space. On the space Rn. And I forgot to say, crucially, again, we still have the involution property. This comes out just for free from varying with respect to the times ti. Okay. Are there any questions up to this point? Okay, so now I want to pass to the Hitchin system and remind you in what sense it's a completely integrable system, and then apply all this machinery to that system to produce a 3 dBF theory. So Hitchin system is an integrable system where the spectral parameter lives on an arbitrary Riemann surface G. And I'll take this genus to be 2 or more for simplicity in this talk. We can also treat the case of 0 and 1 in the paper. These are degenerate cases, so I don't want to focus on them too much for uniformity. So the phase space of the Hitchin system is given by the cotangent bundle of isomorphism classes of stable holomorphic principal bundles on the Riemann surface C. So this is a mouthful. If you don't understand all these words, I'll explain how to think about this on the next slide. The key point is that this is actually a finite dimensional space. And so the cotangent bundle of this manifold, in fact, it's a manifold, and the cotangent bundle of it is a finite dimensional manifold which has dimension 2 times the genus minus 1 times the dimension of the Lie algebra. And why this is, first, to describe the Hamiltonian system, you need to give Hamiltonians. And in fact, Hitchin gave a family of Hamiltonians, which is a complete set of Hamiltonians, through what's called the Hitchin fibration, or the Hitchin map. So this is a bit involved. The way you define these Hamiltonians is as follows. So you want to define functions from the phase space to the complex numbers. So first you define a map from phase space to some space of sections of some sheaf, of some bundle. The way you do this is think about the fiber at any point above a isomorphism class of holomorphic principal bundle. So you pick a holomorphic principal bundle, and then above this bundle, there's a fiber. And this fiber is canonically isomorphic to what's called the Higgs fields. So these are holomorphic 1-0 forms valued in G star. So I call them B in this talk. Usually it's called phi. So these are parameterizing the fiber of the cotangent bundle above a point in the base. So these are the Higgs fields, holomorphic Higgs fields. And so the idea of the Hitchin fibration is to pick a basis of homogeneous polynomials in the on the dual of the Lie algebra G. So they're labeled by 1 to the rank of G, and their degrees as homogeneous polynomials are given by the exponent of the Lie algebra plus 1. So you take these polynomials on G, you apply them to the Higgs field, which is valued in G star. So the polynomials are on G star, so you can apply them to the Higgs field. So you get these sections of these powers of the canonical line bundle. And so these are not yet complex valued Hamiltonians. They're valued in this weird space of sections. But the point is this is a finite dimensional space of sections. So you can then pick a basis of that space. And the coefficients in that basis give you Hamiltonians from the cotangent bundle to the complex numbers. So the point is these are finite dimensional spaces of sections with these precise dimensions. And you can extract from the coefficients in a basis individual Hamiltonians. And the remarkable fact is that the dimensions of these spaces, when you add them up, it turns out to be equal exactly to half the dimension of your phase space. So this is why the Hitchin system is completely integrable. The number of Hamiltonians that you build, which are independent, they coincide with half the dimension of the phase space. Okay. So for our purposes, to be able to connect to the 3DBF theory, we need to use the fact that the Hitchin phase space can be described in a slightly different way, which comes from the fact that you can think about holomorphic principal bundles in a different way. So holomorphic principal bundles are principal bundles where the transition functions are holomorphic. But you can start with a smooth principal bundle, so where the transition functions are smooth. And you can think about the space of G-valued 0-1 connections on this principal bundle. So concretely, what these are described by is in every open patch on the base C, on the Riemann surface C, you prescribe some 0-1 forms valued in the Lie algebra G, and they should connect with each other over intersections through gauge transformations by the transition function. So this is what it means to have a G-valued 0-1 connection on the principal bundle. Okay, so the point is any such 0-1 connection, it defines a unique holomorphic structure on the principal bundle. Why? Because I can always move locally to a local trivialization where the components of A double prime is actually 0. So I can gauge away this A double prime. And in that gauge, if A double prime is 0, in this equation you can see both the left-hand side and the first term on the right are 0. So that tells us that the transition function will become holomorphic. So that's why if you give me a 0-1 connection, I can construct a holomorphic structure on the principal bundle because I can choose a local trivialization where the transition functions become holomorphic. And if I have if you give me 2 such 0-1 forms, then actually they define isomorphic holomorphic structures if and only if they are related by a bundle automorphism. So by a gauge transformation, So bundle automorphisms are these things that act on the connections by gauge transformations. Okay, so that means that I can think about holomorphic structures on the principal bundle as 0-1 connections, but I have to remember to mod out by gauge transformations by the automorphisms of the bundle. So I take this space M of this affine space of G-valued connections. I mod out by the group G of automorphisms of the bundle. This gives me the base of the Hitchin phase space, the space of isomorphism classes of holomorphic bundles. And the nice thing is that this action of the automorphism group on the space of 0-1 connections lifts to the cotangent bundle. So we have a Hamiltonian action of the automorphisms of the principal bundle on the cotangent bundle. And this is a Hamiltonian action with moment map given by this nice formula. So it's valued in the dual of the Lie algebra of the space of automorphisms, of the group of automorphisms of the principal bundle. So just to explain what this formula means, because it will be important in a second, remember that I can think of Higgs fields as elements of the fiber of the cotangent bundle above a point on the base. So here, because I'm now working with smooth principal bundles, my Higgs fields are smooth sections of that same bundle I had before. So they are smooth 1-0 forms valued in G star. Concretely, this means that they are just 1-0 forms valued in G star on every patch. And this is the associated bundle to the principal bundle in the adjoint representation. That just means that on different patches, they relate by the co-adjoint action. The Lie algebra is described in a similar way. So it's global smooth sections of the adjoint bundle. And that means that I can describe them locally by smooth functions on every patch valued in G, which transform across patches by the adjoint action. The covariant derivative del bar A double prime just means taking covariant derivative of this Lie algebra element X. And because it's covariant, I still get something transforming in the adjoint representation. So it's a 0-1 form because I took the del bar derivative. And so I can now pair the covariant derivative of the vector of the Lie algebra element, which is a 0-1 form, with the Higgs field. Because they transform in adjoint and coadjoint representations, they actually pair nicely to form an invariant section over the whole manifold, and I can integrate it over the manifold. So this moment map, if you do the Hamiltonian reduction of the action of G with respect to this moment map at level 0, you get precisely the cotangent bundle of the space of holomorphic principal bundles on G. So this is the phase space of the Hitchin system. I'm telling you that there's an alternative nice description as a symplectic reduction. And this is exactly what we need to apply the machinery I told you about in a second ago, that you can start with a Lagrangian one form on the cotangent bundle, which has this action of G. Provided the Hamiltonians are invariant, we'll be able to gauge this Lagrangian one form to produce Lagrangian one form describing the dynamics on this reduced symplectic manifold. So this is exactly what I want to do now, construct a Lagrangian one form on this cotangent bundle. So I wanted to produce the Hitchin system in the end, so the choice of Hamiltonians to describe the dynamics on this cotangent bundle will be guided by the Hitchin construction. So remember the Hitchin fibration, which took a holomorphic Higgs field and produced, and you apply these polynomials to this holomorphic Higgs field to produce the sections of these holomorphic bundles. And then because I had the basis, I could choose a basis of these spaces, I could just pick out the coefficients in that basis. Now I'm dealing with smooth principal bundles. And as I said, the fiber of this cotangent bundle is now smooth Higgs field. So I can still apply the polynomials that we chose for the construction of the Hitchin map. I can still apply those polynomials to the smooth Higgs field, but I get smooth sections of the same bundles. So I can no longer decompose them into a basis of holomorphic sections because they're smooth. Instead, what I do is I just pick a set of points on the curve and evaluate these polynomials at those points. And you can show that this choice, it provided the set of points as a generic divisor on the curve. This procedure will land back exactly on the previous prescription for the construction of the Hitchin Hamiltonians when the B field becomes holomorphic. So I'm defining a construction here of Hamiltonians on the lifted phase space T star M, which will reduce down to the Hitchin Hamiltonians when you pass to the holomorphic description. So these Hamiltonians are just given by taking the Higgs field, which is smooth, evaluating it at a bunch of points, and then plugging this into the invariant polynomials. So these are my collection of Hamiltonians. There are still n of them because I chose the bunch of points Q to be n in total. So there are n Hamiltonians. Okay, and then the Lagrangian one form is easy to write. So it's just P dq minus the Hamiltonians. So the coordinate along the fiber of the cotangent bundle is B, the Higgs field. And so that's P. And then dq, Q is the coordinate along the base. It parameterizes the 0,1 form on the base. So P delta A double prime is P dq minus the Hamiltonian. So this is just a very canonical Lagrangian one form describing the dynamics of these Hamiltonians on that phase space. Okay. So I want to play the same game as before and introduce some gauge fields. So first of all, remember to write down the action, the multiform action. I need to make a choice of immersion, which describes the n-time dynamic of my fields in the cotangent bundle. So I pull back the Lagrangian one form along this immersion, and I get this object, which is a Lagrangian one form on Rn now. And to gauge it, what I do is, so first of all, I can gauge it because my Hamiltonians are invariant under the adjoint action of the bundle automorphisms. So that means that I have an invariant action under this symmetry group. So I can gauge it by adding the moment map paired with a Lagrange multiplier in the same way as I showed you before in the finite dimensional setting. So remember that this is the Lagrange multiplier is a G-valued connection on along Rn. So now it has this extra dependence on the spectral curve. This is just because I'm dealing with now the Hitchin system where the Lie algebra is really, the Lie algebra is functions from C to the Lie algebra little g. And so there's an extra C dependence in my gauge field. So it's really a gauge field on C cross Rn, which is a connection along Rn. So it has only components along Rn. But the remarkable thing is that if you expand out what this sigma pole L is, you get the kinetic term, which combines very nicely with this moment map term. So I've written out here the moment map explicitly. It's B d bar A double prime acting on A. And these two terms combine very nicely to form the BF action. So in particular, the original 0,1 connection, which describes holomorphic structures of the bundle P, they combine with the one-form connection that describes the gauging to the level mu equals 0. They combine to a connection on C cross Rn, which has all directions now holomorphic along C and all the directions along Rn. So it's a full connection. And its curvature pairs with the field B. So this is the BF action, which emerges very nicely from this construction just by gauging the canonical action on the cotangent bundle. So I should say this is really a multiform version of the 3D mixed BF action, which, as we'll see, describes all the dynamics of the hierarchy of the Hitchin Hamiltonians. Okay, so here this is really a description of the Hitchin system. It's a full description of the Hitchin system, but in terms of smooth data, because the B field is a smooth Higgs field, the curvature or the connection A is a smooth connection, and really the Hitchin system to start with was described in terms of holomorphic things, a holomorphic Higgs field and a holomorphic principal bundle. So I can use the fact that I can always pass to this holomorphic description. Remember that the choice of a 0,1 connection is equivalent to the choice of a holomorphic structure. So what I can do is I can think about a way of trivializing the principal bundle with its holomorphic structure. So let's fix a point P on the curve and a neighborhood U0 of the point. And then U1, which is a complementary open, is just the entire curve minus a point. So the claim is that the holomorphic principal bundle P with its A double prime, which describes the holomorphic structure, it's actually holomorphically trivial on both opens. So on U0, this is because U0 is a small open and it's locally trivial. And on U1, this is because there's this deep fact that holomorphic principal bundles on non-compact Riemann surfaces are always trivializable. So my holomorphic principal bundle is trivializable on both of these opens, U0 and U1. So that means that I can move to local trivializations in both of these patches where the holomorphic structure A double prime is equal to 0. Okay, and remember what that means is that in that local trivialization, the transition functions between the two patches are given by holomorphic functions. So really here they're holomorphic along C. There's an extra Rn dependence that's creeped into the story because of this gauging procedure. But really what I have is a bundle living on C cross Rn, which is a principal bundle with group valued transition functions, and they're now holomorphic in this choice of trivialization. And what I also want is the gauge field, or the Higgs field to be holomorphic. And I can achieve that by imposing the constraint mu equal to 0, because mu, remember, is this constraint. And so if I set it to 0, I'm really saying that in the gauge A double prime equals 0, I'm saying just del bar B is 0. So B becomes holomorphic. Okay, so I'm now dealing with a holomorphic transition function for my bundle. So it's really a holomorphic principal bundle. And the Higgs field, which parameterizes the fiber, is now holomorphic by solving this constraint mu equal to 0. So it's given by two holomorphic functions on a patch U0 and U1, which are connected together by these holomorphic transition functions on the intersection. Okay, so now I can derive the action for this in this holomorphic description. So this is a non-trivial statement. So I claim that if you start with a 3dBF action that I showed you before, and you move to this holomorphic description where the gauge fields, or the transition functions become holomorphic and the Higgs field becomes holomorphic, then the action turns into the following. So the BF term becomes this piece. And the reason it's non-trivial is because here you have transition functions appearing, which are living on intersections of patches, whereas before I just had a pairing between the B field and the gauge field, which were living on opens themselves. So there's a non-trivial step happening here, and you can read more about it in our paper. But this is the result of the reduction to this holomorphic picture. And what's really nice is if you derive the equations of motion for this action, which is again quite non-trivial, well, for the different fields in the action, you get the following. So first, varying the action with respect to L, you get the existence of some G-valued function on the open U and a meromorphic G-valued function on U1 with simple poles at the QIs. So QIs were the points where I inserted the Hamiltonians, which I used to construct the Hamiltonians. So these meromorphic and holomorphic functions valued in G, they're connected on the overlap by these gauge transformations by the holomorphic transition functions. And if you vary the action with respect to the transition functions, you get the Lax equation for the Higgs field. So this is really the Hitchin equation written in Lax form. So it tells you that the evolution of the Higgs field with respect to all the times is governed by the Lax equation, which is the commutator of these matrices M with the Lax matrix, or the Higgs field. And this is true in both patches by virtue of this transformation property of these M's. Again, as usual, the variation with respect to the times gives you the involution property of the Hamiltonians. So it's really rebuilding the whole Hitchin system. And the stability condition that I assumed about the holomorphic principal bundles, they lead to this condition that the matrices which emerge from the variation with respect to L, they form a flat connection on multi-time space. And this is a key property of these integrable systems or integrable hierarchies, that the matrices M which appear in the Lax connection, or in the Lax equation, they should form a flat connection on multi-time space. So this is really the equations of motion for the Hitchin system formulated in the Lax formalism, which are derived from this action. So let me summarize, because I'm out of time. So what I showed you is how to derive a variational formulation of the full Hitchin system, namely the whole hierarchy of the Hitchin system, by starting with a very canonical action on the cotangent bundle of the space of 0, 1 connection on a smooth principal bundle, gauging this action by noticing that it's invariant under the action of the bundle automorphisms. I gauge this action to get the 3dBF action. And then, so this describes the Hitchin system already, but in terms of smooth data, so smooth Higgs fields and smooth bundles. Then I can pass to the holomorphic description to get a description of the Hitchin system in its original description in terms of holomorphic data. We can also generalize all of this to Riemann surfaces of genus 0 and 1. And we can also add extra marked points where the Higgs field is allowed to have poles. So we get meromorphic lax connections. And we can produce very explicit examples of rational and also elliptic Godin models. And so this is the genus 1 case, and the elliptic spin Kalager-Rimoso model as a special case. So natural questions which follow from this work is, can we use this Lagrangian formulation of the Hitchin system, specifically of the whole hierarchy, to possibly quantize the hierarchy of the Hitchin system by using possibly some path integral methods extended to the multiform setting? It would be very nice to figure out if what I told you today generalizes to these high dimensional settings. So can we find, for example, multiform versions of the 4D, 5D, 6D Chern-Simons actions, and derive from that some multiform versions of the Lagrangian formulations of these integrable hierarchies in 2, 3, and 4 dimensions. And also, all of this worked for high genus Riemann surfaces. So the natural question is, can you extend also the construction in high genus in a similar way to what we've done to high genus in higher dimensions? Okay, thank you.
Thank you very much for your talk. Nice talk. Do we have some questions? In the back. There's another one first. Okay, so you're number 3.
I had a question if you have an idea on about how to embed in string theory this construction, if you have an intuition.
Yeah. So I'm afraid, my talk was not at all about string theory. I mean, I know that there are ways of embedding 4D Chern-Simons into string theory. I think there's also 3D. So Gayota Witten did some work, I think, on how to embed 3D mixed BF into string theory. So there's work on this. I'm just not very familiar with it. You can, I think, do this. Yeah.
Okay.
There was a question. Sergey had a question, and then Arkady had a question.
I have a couple of questions. Is there an integrable deformation of Hitchin system to the case where the phase space is a Heisenberg double?
Is there what?
Integrable deformation of Hitchin system.
Where the phase space is what, you said?
The Heisenberg double. Not the tangent bundle, but...
Yeah, that's a good question. I haven't thought about it. Yeah.
And can you also consider elliptic spin Roy-Genard-Snyder model?
Is it a Hitchin system?
No, it's...
Okay. So we haven't thought about it, but it's a natural question. The question is, can you describe it from 3dBF? I'm not sure because...
Think about it as a deformation of elliptic spin Kaloger.
Yeah, okay, as a deformation, yeah.
And it's a relativistic invariant. It has a relativistic invariance.
Yeah, these are all very natural questions I don't know the answer to. I haven't thought about them. Yeah, we can discuss them.
So very naive question. So Hitchin system you can get from self-dual Young-Mills by reduction. Is there any implications for self-dual Young-Mills? Because you can get self-dual Young-Mills from BF system as well.
Yeah.
You can uplift it further.
I think in all these stories, if you go higher in dimensions, you get broader and broader classes of integrable systems, which can then reduce down to the systems you get from lower dimensional theories. So 3dBF is at the very bottom. So probably you can get it from reduction of, what did you say? Is it 60 holomorphic Chern-Simons or? Four-dimensional. Yeah, so 4-dimensional BF would be, I think, a special case or a special limit of 4D Chern-Simons. Holomorphic 4D BF is a special limit of 4D Chern-Simons. And then there's a reduction, which is quite natural to 3D BF theory. So maybe there's a link to.
Do you expect that quantizing the Hitchin system would be equivalent to quantizing this 3D theory?
Yeah, that's a good question. That's the kind of question that we want to address. It's a very simple setting compared to 4D Chern-Simons, so it's a natural setting to start addressing these questions properly. Yeah. So the system you're dealing with is finite dimensional. the 3dBF theory is a lot simpler than 4D Chern-Simons. So yeah, you can play the same games that you like to play, but in this one-dimensional less. And it's a natural question. Yeah, the question you ask is quantizing the Hitchin system the same thing as quantizing 3dBF? You could try to answer this question. We don't know yet.
Thanks.
Yeah.
So thank you for the nice talk. There is a relation between Hitchin moduli spaces and four-dimensional theories with n equal to 2 supersymmetry, which was explored by this work by Gaiotto, Moore, and Neitzke about a decade ago. And they led to a relation with integrability, and in particular, there are thermodynamical Bethe-ansatz type of coordinates on the moduli spaces of the Hitchin system.
Yeah.
Do you have a comment? Is there a relation? Does this construction that you have by something in that direction? Or?
It's a very good question. I haven't thought about it. So the point is Hitchin appears in many different contexts. That's one of them. So it's natural to explore whether this has anything to say about that story. Yeah, it's a great question. We can discuss it. Yeah.
So my question is a little bit twofold. One is attached to his question. I think that what is talking more naturally is the higher dimensional, four-dimensional Hitchin system, because this is the case of GMN, as far as I can understand. So you are dealing with a reduction. You are doing something in 3 dimensions. So you should get some reduction of the GMN space, possibly, if something works. Is that correct?
Yeah, but I thought Hitchin system appears directly in the GMN construction, maybe through a reduction, but it's certainly there explicitly. So I think there should be a link to 3dBF as well, not only through 4D Chern-Simons. Yeah.
Okay. You are ready? Okay, very good. So it's a pleasure to introduce C.K. Yang from Nordita, and he will speak about a BPS road to holography and matrix theory.
Thanks a lot, Charlotte. Sorry. Anyway, this is the... Okay, that's working. So I would like to start with thanking all the organizers for bringing all of us together, and of course for inviting me, for which I'm very much honored. So apparently I'm going to discuss a BPS road, which might sound a bit mundane, but I promise that there are some surprises on the road. Okay, I'm already spoiling the surprise. But anyway, so this talk will be based on my recent works through the past 2 years in collaboration with a by now quite sizable community. So I'll be mostly focusing on this set of papers and work in progress, but also borrow important key insights from my other recent works in collaboration with a group of people, and many of them actually sitting in the audience. I have to apologize, I cannot really go through all the names here, but I do like to refer to Truls Hammerk's talk tomorrow on narrativistic string theory, which really provides a complementary perspective of what I'm going to discuss today. No? Sorry. Apparently, I don't know how to use this. Somehow it jumps all the way down. Okay, now I'm learning. But anyway, I guess I've spoiled the whole talk already. But anyway, so, wait, what is happening? I didn't do anything. It happened again. It just likes me to jump all the way to matrix theory. Maybe I should point to somewhere. Okay, hopefully now it's working. So start with the take-home message of the whole talk. Maybe it's because when I press this button. Okay, avoid that. Which is the following. There is, at least I think, quite interesting and novel no-Lorentzian perspective that was somehow missed out on the ADS-CFT correspondence. And we were actually led to discover this by following this BPS road. And this might already sound confusing to you because you might say that isn't ADS-CFT one of the most relativistic theories that we can think of? So what is no-Lorentzian about it? Let's take a simple example. Well, it's not simple, the classic example of ADS5 CFT4. Then we have this bulk geometry ADS5 cross S5. And now if you go to this asymptotic infinity regime, you'll see various singular behaviors in 10 dimensions. So normally we're focusing on 4D, where we see these encores for supermills, that is due to gravity on this ADS bulk. But when we start thinking about this 10-dimensional geometry, that becomes singular. And that is where these no-Lorentzian geometric insights will be helpful. And this perspective is especially important exactly because it makes this BPS nature of both holography and matrix theory very manifest. And using this perspective, we can form a framework to classify holography in string theory, not only for the ones related to an ADS bulk geometry, but also for the ones related to possibly the Sitter, flat space, and even no-Lorentzian bulk geometries. And moreover, this no-Lorentzian perspective provides us a chance to revisit this finite n version of BFS conjecture for matrix theory, which I think is very much complementary to the recent revival of matrix theory from both communities of amplitudes and conformal bootstrap. And also there was this very nice talk by Jackson Fliss yesterday from the perspective of entanglement entropy that I have learned about. Okay, so first the holography part. Now it's working, so that's good. No? Okay, I said that too early. Maybe the battery is down, maybe that's why. But anyway, so let me start with illustrating this no-Lorentzian perspective by starting with the classic example of ADS5 CFT4. And here I'm just giving you the full bulk geometry, that is this 10-dimensional ADS5 cross S5. And I have introduced this parameter omega, which is proportional to the square of the radial direction r. So now if you go to this asymptotic infinity regime, where essentially sending omega to infinity. And now if you look at this line element, you'll see that it becomes singular. So that is where this 10-dimensional metric description becomes invalid. And this is exactly where you see this no-Lorentzian geometric description becomes useful. So we actually end up with a 10-dimensional Galilei-like geometry where I have a Galilean type of boost that maps the transverse sector to the longitudinal sector. There's yet another interesting regime, which I won't have time to talk about. That's when you send this omega to 0. So if you think about the thermal case, you're basically zooming on these horizons associated with the black brane. So probably not surprisingly, we'll see this effective geometry that is Carroll-like. But let's return to this asymptotic infinity regime. What I have said might not be very satisfactory to you because all you can see at the moment is that there's some 10-dimensional geometry that becomes singular. So you might ask the question, if we say that this is Galilei-like, well, is this manifest the Galilei-like boost symmetry? In order to understand that, let's look at some, sorry, it's just slow. Maybe I'm standing too far away. Oh, no. No. Maybe I can just use the computer. Is that... Okay, I'll do that and you can do your job. So let's try to understand this by looking at something that is more physical. So in this ADS5 CFT4 case, it's natural that we think about a probe D3 brane. So here I'm just giving you the volume, thank you, action. Okay, now it's perfect, thank you. Which is right here. So this is the wall volume action describing D3 brane, a probe D3 brane on this ADS5 cross S5 background. And you can see that it's reparameterized in terms of this parameter omega. So now if you send omega to infinity, that means we're going to this asymptotic infinity regime here. It's really a reparameterization of the famous Model-Sena limit. But if you really zoom in, you'll see what is happening is that the effective mass associated with the D3 brane is blown up. However, this divergence is exactly cancelled by a fine-tuned D3 brane charge. And that's, of course, because of the underlying supersymmetry. So after all, what we're really doing is by taking a BPS decoupling limit, zooming on a background D3 brane. And the leftover modes are exactly these neo BPS states, which are also well captured by this limiting procedure. So here I'm just talking about a single D3 brane, but you can also consider a stack of coinciding D3 branes, in which case we're not abelianizing this free action to be exactly n equals 4 superamines, that is corresponding to gravity on this background ADS5 times S5 geometry. But for simplicity, let's just focus on this single brane case. And there you can check explicitly that this is really invariant under this Galilei-like boost transformation up to some boundary term. So what is happening here is that by taking this BPS decoupling limit, we have blown up a background D3 brane, which leads to this spontaneous symmetry breaking of the space-time symmetry. And we're left with this geometry, where I have a four-dimensional sector aligned with the background D3 brane, which kind of replaces the absolute time direction in Newtonian physics. Moreover, we have this six-dimensional transverse sector that is mapped to this four-dimensional longitudinal sector with this Galilei-like boost symmetry. Okay? So in a word, this n equals 4 superamines that are super familiar with actually sees a 10-dimensional Galilei-like geometry. Moreover, if you compactify, maybe the problem is really about me. Okay, I'm sorry. So if you compactify these D3 branes over some internal 3 manifold, and for simplicity, let's take it to be a 3 twirls. Then I have these wrapped D3 branes interacting with each other. And now the gravitational force is really Newton-like instantaneous force. Moreover, you can TDualize on these 3 twirls. So that's the standard relation that maps n equals 4 superamines to be n equals 16 superamines in 0 plus 1 dimension, which is precisely BFSS matrix quantum mechanics. And this T-duality also maps the D3 branes, the wrapped ones, to D0 particles, whose dynamics is described by BFSS matrix theory. So what we end up with is actually the picture of a bunch of relativistic D0 particles interacting with each other with these Newton-like forces. But holographically, it becomes a bit more complex. So the original ADS5 geometry is now mapped to this conformally ADS2 geometry together with an 8 sphere. But this geometry is only good for region. And that's because there's a key difference here. The dilaton has developed some profile, so it's a function of this radial direction. And now if you go to the center of the bulk, you'll see that the string coupling really grows and you're actually entering the M3 region. But this is nothing but this modern holographic perspective of the old BFSS conjecture, which says that the larger limit of BFSS matrix quantum mechanics describes you the full M3 in an asymptotically flat spacetime. This is always very difficult. Okay, it's still working. But there's actually also some interesting property of this infinite omega limit. Actually, after you take this essentially BPS decoupling limit, you'll see an emergent dilatation symmetry, which means even though we have taken this omega to be dependent on the radial direction, but actually it doesn't matter what kind of detailed form this omega takes. For simplicity, you can even take this omega to be a constant. But that leads us to a change of philosophy. So I have been saying that this no-Lorentzian feature rises by going to this asymptotic infinity regime of the ADS bulk. But there's more to it. And now you can actually think about applying this BPS decoupling limit to a full-fledged string theory. In this case, it will be type 2A superstring theory. So what we do is the following. We take type 2A superstring theory and reparameterize all the background fields in this particular way with a constant omega. So if you send omega to infinity, you'll still get the same theory. So here I've been sticking to a flat spacetime, but actually you can also make it curved, which I'm going to do near the end of the talk when it becomes actually necessary. And now if you take this BPS decoupling limit by sending omega to infinity in the full type 2A, you should be led to this self-contained corner that is also a full-fledged string theory. And I have to give a name to it, so calling it matrix zero brane theory for obvious reason, and M0T for short. And please do remember this acronym because I'm actually going to use it for the rest of the talk. So what it describes is essentially, the dynamics is captured by these light excitations that are these zero branes, whose dynamics is described by BFS as matrix quantum mechanics. But because we say this is a full-fledged string theory, we should also consider other extended objects, for example, the fundamental string. Except that, as we'll see very soon, this fundamental string won't be fundamental anymore. It doesn't have vibrations, so it's highly no-perturbative. And in that sense, this M0T is really a no-perturbative string theory. Okay? And moreover, this omega going to infinity limit that leads to M0T can be further interpreted as an infinite speed of light limit by sending this C to infinity. To understand that, let's again focus on a probe D0 brane in this theory. So we start with the D0 brane in type 2A superstring theory, which is nothing but this relativistic particle coupled to some U1 potential. So I have recovered all the dependence on the speed of light c. Moreover, I have fine-tuned the charge so that it's canceling the divergent D0 brane mass mc squared when c is taken to infinity. And after a trivial rewriting, you can see that the reparameterizations of the dilaton, line element, and Raman 1 form are matched on to these reparameterizations of the background fields that we introduced earlier, as long as you identify omega with C. So now if you take this BPS decoupling limit by sending C or omega to infinity, you'll get these new BPS states described by this relativistic particle action. And again, if you instead consider a stack of D0 branes, you'll now abelianize this theory to be BFSS matrix quantum mechanics. Okay, so this procedure sounds like the usual relativistic limit of relativistic particle that gives you Newtonian physics. But there's a key difference. So there, we always have a rest mass, mc squared, that we just set aside. But here it's very important that this rest mass is cancelled by the critical charge, so that we have underlying supersymmetry protecting these BPS conditions. Okay. Now it's the nightmare again. Maybe I just have to be close by. But as I've said, this M0T is supposed to be a full-fledged string theory. So let's also look at some other modes which are not the D0 branes. For example, this fundamental string. And we kind of already know how to get this M0T fundamental string from the usual Polyakov action. And here I'm just going to focus on this bosonic sector. So what we do is again that we recover all the dependence on the speed of light and then send this C to infinity. So that's the same as sending omega to infinity. But there's a key difference here. So we no longer have any critical charge that we can use to cancel the divergence from this sector. And that's why we still have divergence in the system, which leads to these constraints that are imposed by introducing this Lagrange multiplier that are called lambda. Okay, so this is exactly the reason why the string becomes node productive and it's actually node vibrating. And you can check that the target space geometry is indeed satisfying this Galilean type of boost symmetry. And moreover, the wall sheet is also non-Lorentzian in this case. And that's because there's a no trivial dependence on the speed of light on the wall sheet. Topologically, what it does is that it introduces various pinchings on the Riemann surfaces. And we're actually led to these string topologies, which are pinched, that are used in amplitude string theory to compute string amplitudes. But this is not a coincidence at all. So in fact, if you consider this T-duality along time-like direction, which was pioneered by Chris Hall in the audience, and in this case, you apply it to this M0T fundamental string. So you can derive this new action, which is actually the same one as you can get by sending the tension of the string to 0 in usual Polyakov string theory. So this leads us to a tensionless string theory, and that's actually coming from here in Sweden. So now, if you further go to this ambitwistor string gauge, you'll recover, at least classically, this chiral sector described by ambitwistor string theory. That explains the similarity at the level of the wall sheet, and it's because T-duality doesn't really change the wall sheet structure. By the way, this is actually the same type of limit that Bo Songbori and Lawrence Eberhard already discussed in the next talks. Okay. But if you think holographically, this actually implies something I think quite interesting. So let's go back to the M0T string. In that case, we know the fundamental string doesn't really capture the light excitations. Instead, you have to focus on the D0 branes, and therefore BFSS matrix quantum mechanics. So when you think about the time-like T-duality, you should really apply it to BFSS. And that leads us to IKKT matrix theory on instantons. Holographically, you'll see that the bulk geometry should be flat space. I think friends Cecilia will be discussing something related to this tomorrow, so I won't say too much about the precise relations here. But furthermore, if you start doing these more regular space-like T-duality transformations, you actually be led to this de Sitter-like bulk geometry a la Chris Hall. And now if you go to this asymptotic infinity regime, you discover 10-dimensional chiral-like geometries. So in some sense, this time-like T-duality transformation is really like a looking glass that tunnels us from ADS-FT to other type of holographic constructions. But the story doesn't stop here. So let's just ponder over what we have done. So what we have done is that we started with the bulk geometry that is relativistic, and we went to this asymptotic infinity. But you can also reverse that, and that's actually the true power of this whole program. So instead of starting with the bulk, it's actually easier to start with the BPS decoupling limits. And you can classify these BPS decoupling limits by really understanding the no-Lorentzian geometry behind them. And then there's actually a well-defined deformation that is due to the TT bar deformation that Roberto was reviewing very nicely earlier this morning. And they'll generate you this bulk geometry. In this case, they're relativistic. But also, you don't have to stop there. Not only you can apply a single BPS decoupling limit asymptotically, you can also apply a set of consecutive BPS decoupling limits. And these limits are actually well organized by what we call DLCQ, that is short for discrete Lycon quantization, that I'll discuss a bit more later. And there's actually this very prescient work from 20 plus years ago, which is unpublished, where they already understood this type of perspective, but from the BPS mass spectral. And now we're blending in this geometric interpretation, which is no Lorentzian. And in this case, now if you turn on this generalized TT bar deformation, I forgot a key sentence. So in general, holographically, this BPS decoupling limit will be mapped to a near horizon limit in the bulk that leads to this set of geometries. But in the most general setup, you don't need all BPS decoupling limits to be mapped to near horizon limits, but instead you just need a portion of them be mapped to near horizon limits, and the remaining are still the BPS decoupling limits that I have seen asymptotically, and they'll lead us to this no-Lorentzian bulk geometry. And this provides us a chance of understanding possibly no-Lorentzian holography from top down, which has been explored quite a lot recently. Okay, so this is basically what I want to say about the holographic part of the story. But before I move on to matrix theory, I think it's necessary that I say a few words about the M-theory uplift of M0T, which I hope will help you understand what is going on. So again, I'm showing this M0T limiting prescription parameterized by this constant omega. So if you send omega to infinity in type 2a superstring theory, you'll get M0T. I'm just repeating what I have said for multiple times. But for this prescription, before you take the limit, it's easy to uplift to 11 dimensions in M theory. So this is just the standard Kaluza-Klein reduction, where we compactify M theory over this space-like circle that we call Y. Oh, I already don't have any time. Oh, thank you. That's a -1, that's why. In this case, you can, there's an interesting question that you can ask. What if we apply this infinite omega limit at the level of this 11D? That actually turns this space-like circle into a light-like circle, which means that it led to the so-called discrete light quantization of M3, well, DLCQ is short for, well, and for short we call it DLCQ. And this is just a fancy way of saying that we have a light-like circle here. So now if you do this null compactification, you'll get back M0T. So normally you'll think that this light-like circle is quite exotic, but actually in string theory or M theory, you can utilize it so that it's mapped to a space-like circle, except that the target space geometry now becomes no-Lorentzian. And in this case, the light excitations are exactly the Kaluza-Klein modes in this light-like circle, so that they are mapped to D0 particles in M0T described by BFSS. Okay, so finally we can move on to the matrix theory side, but I guess I have to speed up here. Sorry. Okay, so let's first review a bit the original BFSS conjecture, which says the following. You start with a bound state of n D0 particles in M0T, which is described by this matrix quantum mechanical theory that is n equals 16 supermills in 0+1 dimension. From the M theory perspective, you have this supergraviton instead of the D0 branes with the discrete light-like momentum. In the large n limit, this light-like momentum becomes continuous, and that's when you see a decompactification limit. And hence the conjecture, the large n limit of BFSS should describe as the full M theory in asymptotically flat spacetime. Okay? So we can test this by thinking about this iconal scattering between bound states of D0 branes. So there has been quite a lot, very exciting new developments on understanding the non-perturbative aspects of BFSS as well as its BMN variants. But here I'm actually just going to focus on this old school perturbative calculation back in the days. So what we're computing is this iconal scattering between D0 branes, where we have one bound state of N1 D0 branes and another bound state of N2 D0 branes. We also go to this rest frame, where this first bound state is at rest, and the second one is moving at the speed v. And we take the impact parameter to be very large and the potential to be very small. Okay, and then you can go through the calculation, which is done in these very nice papers and also explored in many other papers that I haven't cited here. And eventually, what you can compute is this effective potential between the bound states. And I'm only giving you the one loop result here, which I'm going to use later. Okay, and this calculation, when BFSS is perturbative, is valid when the effective coupling is small. That means finite n and small radius for this light-like circle in M3. But that's exactly when this 11-dimensional supergravity fails. However, if you do Petoff-T supergravity calculation, it seems that it does work for this 2-2 scattering. So let's try to understand why this happens again. No. Sorry about it. So now we switch to this Petoff-T 11D supergravity. Well, instead of having the D0 particles, we have the supergravitons. And if you take N1 to be much larger than N2, you'll say that, okay, this is a source particle and that's a probe particle. So I can just backreact these supergravitons to get this Eichelberg Saxion metric. And then when I consider the motion of this second supergraviton in this potential, we can compute this effective potential. So this is done in this very nice paper by Becker, Puczynski, and Zetlin back then. But now if you look at this Eichelberg Saxion metric, it gains this deformation that depends on omega. Okay? But that means we're actually not having a DLCQ because this X minus is actually space-like. So now if you do a dimensional reduction to type 2A, you'll see that we're actually back to this conformally ADS2 geometry together with an A sphere. So in some sense, we're back to holography. And this works when the string coupling is very small, and also when you have large n, so that the effective coupling for BFSS is large. So what I'm doing here is that when you say there's a Petoff-T calculation in BFSS and a Petoff-T supergravity calculation, we're really computing things in different energy regimes. And usually you don't expect detailed dynamics to match, but because of holography, you do expect protected objects, for example, this 2-2 scattering, to work out. So probably it's not surprising that if you go to high order terms, there are actually clear mismatches. Okay? But this has been known, and it seems that we should just try to improve our understanding of the large n limit of BFSS, which is actually happening right now, and there are many different efforts towards this. But to me, there's also another important question. You can also ask, what is this Petoff-T / finite n BFSS matrix theory? We know that, okay, this is 11-dimensional supergravity in DLCQ, and you compactify it along this lilac circle and shrink the circle to be very small. But this sounds very singular. So the usual take is that this is just like a very singular thing to consider. Thank you. So probably it just doesn't make sense. But now with our new insights from no-Lorentzian geometry, we can say that this is singular, that's true, but in an understandable way. It should lead us to this no-Lorentzian M0T supergravity, at least for the effective gravity description. There are also other modes. Okay, so what does that mean? So I have talked about this M0T prescription before in flat space-time, but now I have to make it curved. But that's pretty straightforward. You can just borrow this nicely developed Newton-Gacton formalism in Newtonian gravity. So you take the absolute time direction and covariantize it by introducing this temporal Villeurbanne field. And moreover, we can introduce this spatial Villeurbanne field to form a metric that is transverse. So this is not a 10-dimensional metric because it's of rank 9. And even though we don't really have a metric description anymore, but we can use this geometric data to covariantize our flat space M0T prescription to be something like this. So you can see that in this Ramon sector, we have the critical part, but also a finite piece in omega. And that's exactly acting as the Newton potential in this no-Lorentzian supergravity. So now if you plug this set of answers back into type 2A supergravity and take omega to infinity, we expect that we should be able to rid of at least some interesting dynamics from it. But this is still an ongoing project, so there's still many things that are unknown for this M0T supergravity, but I think that's also exactly what makes it exciting. It's such a new theory in some way. But before I go to the dynamics in the last slide, let me just recap a bit. So what we're observing is that if you think about a finite n, or I should say small n, BFSS, it's really a D0 particle volt line formalism for this 10-dimensional no-Lorentzian quantum gravity. And this observation is further supported by this U-dual frame to matrix string theory a la Motel, Dijkgraaf, Verlinde, and Verlinde. And this is essentially a second quantization of what we call narrativistic string theory. And again, one of the original work is also from Sweden, but it's referred to as want string theory there. And this theory arises by taking this BPS decoupling limit to zoom in on a background fundamental string. And that leads us to a perturbative string theory that is unitary and UV complete. So you can apply standard CFT techniques to compute things here. And then you can map these physical observables you can compute here to understand this M0T. Okay? Okay, so as I have promised, we can actually read off some interesting dynamics, at least, by following this route. So since we're talking about the Newton-like gravity theory, so you ask, what is the Poisson equation that encodes the dynamics there? And this is what you can do. You take type 2A supergravity coupled to D0 particle, so that's relativistic. And the Poisson equation arises by varying this action with respect to this omega parameter that I have introduced, which controls the BPS decoupling limit. And then you send omega to infinity. And holographically, this is like starting with the radial flow equation and push it to asymptotic infinity. Indeed, you read off this second derivative term acting on the Newton potential. On the source side, you can see that first two leading order terms are exactly cancelled, and you're left with this sub-leading order term, which precisely reproduces you this V to the fourth dependence. And V is the relative velocity between these two bound states of these branes. And we should only view this as a proof of concept, because if you really want to go to higher order terms, we still need the full perturbation theory of these branes in M0T supergravity, and that's still to be developed. But I think it's better that I end at this open question. Thank you. Because I believe that this is a new arena that we can play with many old ideas, but with a new twist, and there are really a lot more to explore. Thank you very much.
Thank you very much for this nice talk. Do we have some questions?
Thank you. Thank you for a nice talk. Actually, I'm a bit surprised that you say that finite n BFFS matrix model is a kind of quantization for non-Lorentzian supergravity. I would say it should be just for Lorentzian gravity.
Yeah.
Because in principle, because there exist covariant versions of this matrix model in 10 dimensions and in 11 dimensions, supersymmetric and with Lorentz symmetry.
Yeah.
If you take one particle limit of BFSS, it is just, okay, you quantize particle in 11 dimensions, say, you should obtain 11-dimensional supergravity, and this is Lorentzian gravity.
Yes, thank you for the question. So that's exactly the normal take for BFSS, but that works in the large n limit, importantly. So the thing is that if you think about finite n, like a small n actually, then the D0 branes do not backreact into this relativistic gravity. But when they start backreacting, you'll get back.
It works even in n equal 1.
In what sense?
You have just one.
Yes.
One particle.
In what sense that you get?
It's a gauge fixed version of just much less superparticle in 11 dimensions.
Yeah, but the thing is that if you think about a single,
is normal supergravity.
Yeah, so if you think about a single D0 brane, then you really get showed it earlier. You really get a relativistic particle action. So if you think about what is probing
in your limit,
but would you agree that this is a?
It can be considered as a gauge fixed version of relativistic particle action.
Okay, maybe we should discuss more that later. Yes, thank you.
Thanks, Iggy. So one just outlook question maybe. Have you thought about the equivalent Carolian supergravity construction?
Yeah, so well, these Carol-like structures arise in various places, as we have seen very naturally in this framework. So it could be arising as this asymptotic infinity limit of the theta. And there you can already think about Carol-like gravity.
What is supergravity? So this last slide you showed with the M0T supergravity construction, did you have?
Yes, but as Chris Hall realized a long time ago, this is actually a different regime. So there's this type 2 star theory where you have instabilities. But it will be interesting to understand what kind of twists that they have if you think about this supergravity theory that is Carol-like. And there's yet another region which is more closely related to your own work. So if you go to this near horizon limit, you'll get this Carol-like structure that is not really, I mean, okay, this is not really BPS, but it has a BPS feature. But there you just don't have BPS feature at all. So there'll be another twist.
Thanks.
Thank you. Thank you.
One, two. Yeah.
All right. Okay. All right. Thank you. I think we can start. So I was tasked by the organizers the role of chairing this session. And before we start, I wanted just to say a couple of words about what this session is about, because that's something that is probably floating on everybody's mind. So the point of this session is that so these are challenging times for our community, no? And we are all faced with this at every career level. Okay, thank you. Sorry. So I have to repeat. So I was tasked by the organizers the role of chair of this session, and I wanted to say a couple of words to introduce what this session is about. With the organizers, when we organized this conference, one of the things that floated in our mind is that indeed these are challenging times for our community, and they are challenging at every level. They are challenging for juniors up to seniors. And the major challenge is that the community now needs to provide fundings for research. No, like and that's an important thing. This conference is existing because we have the support of the COST network. The COST network will be over soon, and the grant is going to be over, and we need something that will replace it. And so one of the aim of this session is maybe we will get somebody that we can start forming the core group for the next COST application or something like that. And so since we are facing this challenging time, it's important to be aware of all the funding opportunities there are. And it's important that it's part of our job also to apply for these things and try again until we are successful. And so, of course, every European state has its own set of grants and strategies for funding research, and we couldn't overview all of them in this session because it would have been impossible. But there are luckily some universal channels which are well established by the European Union, and so in this first part of the session we'll have Pascal Anastasiopoulos from ERC-EA that will present some of the funding opportunities in Europe for us. And then Alessandro Sfondrini from Padova, well, we all know him. He will speak about the COST opportunity. And then we will have a panel discussion among these two presenters that will be joined also by Yolanda and Oliver, that will speak about their own experiences in applying and what were the challenges, what were the motivations that they had to drive them to do that. And then hopefully we'll have some Q&A from the audience, or with some comments, some suggestions, maybe some remarks even on the status of the field and these challenging times. So okay, without further ado, I give the words to our first presenter, is Pascal Anastasiopoulos. Thank you.
Thank you very much for the invitation and the opportunity to present the funding opportunities in Europe. Actually, the table of the content of this talk will go as follows. I will give a small introduction. I will talk about the Marie Curie actions, but this will be very short because I'm not working for REA, which takes care of the Marie Curie. Then I will talk about the ERC, some general stuff also, and I will try to somehow give you some hints for those who are planning to apply, and then I will close. So Horizon Europe is the main research funding scheme and runs from 2021 to 2027. It focuses on innovation, mobility, and frontier research, and has two main schemes: the Marie Curie actions, and where the total budget for this period was 6.6 billion, and the ERC, which is 16 billion. Now, of course, after the 2027 should be a new program, which is going to be written soon. Now, what do these schemes do? The aim of these schemes are to support excellent research and researchers. They encourage international and interdisciplinary collaborations. They promote research visibility, career development, and they are based on a competitive peer review evaluation and provide strong prestige and recognition. Now, this is our general points that both share in some sense, but there are also how this happened. Okay, I have to go back. Okay. So, okay. So, but there are some differences in the approaches of the two grants. One focuses on the mobility training and career development, the Marie Curies. They target researchers at the early stage of their career, so PhDs, supports PhDs and postdoctoral researchers. The grant type is individual and network mobility. The funding, the Marie Curie funds the salary, training, and networking. The duration is from 1 to 4 years, so it's a kind of fellowship. And the evaluation is based on excellence and the training impact that this grant can give. On the other hand, the ERC focuses on frontier research excellence. It targets independent top researchers. It gives the possibility for someone to build his team and covers the team and equipment. Usually it's from 5 years and 5 years and on, so it's a grant, and it's based on the excellence and the breakthrough potential of the application. This is the only slide that I have for Marie Curie, because as I said, it's not my field. There are these actions, doctoral networks, so which the point is that to train PhD students. Postdoctoral fellowships in order to help the training and the development of the postdocs. Also, there are staff exchanges which help for knowledge transfer in academia, but also outside. Co-fund, so these actions are they co-found local, regional, and national programs. And finally, there are some programs that they fund the public outreach, which I think is pretty important to communicate our research to others. Now, the main thing, at least from my side, the ERC. Now, some general stuff about the ERC. The ERC is governed by scientists, so scientists for science, scientists for scientists. So it's governed by the Scientific Council. ERC means European Research Council. So this is formed out of 22 scientists. And they have the full authority over the strategy of the ERC. It provides scientific freedom. Scientific excellence is the only criterion. It supports individual scientists. There are no predetermined subjects for the ERC. Support for frontier research in all fields, science and humanities. I will give more next slides. And actually, all this process goes through an international peer review evaluation. So the evaluation, as I say, is based on excellence, and this is the only criterion. When I'm talking about excellence, I'm referring to excellence on the research project. It has to have great breaking nature, potential scientific impact, on the excellence on the scientific approach, but also excellence of the principal investigator, the capacity, the intellectual capacity of the researcher, the creativity and the commitment. On the other hand, what I should mention is that the last years there is a shift of this excellence on the research project. When you are going to apply, you should really focus on the project. And of course, there is a part for which you will present your CV, etc. But this part is more to show that the person who is applying for a grant is able to achieve the goals of the project. I will comment again on that, but what I want you to remember from this slide is that the excellence for the ERC is based on the research project, primarily. Now, the schemes, the ERC grant schemes are these. The starting grant goes from 2 to 7 years after the PhD. It's up to €1.5 million, and it lasts for 5 years. The consolidator grant, 7 to 12 years after PhD, and it's up to 2 million, goes up to 5 years. Advanced grant for established researchers goes up to 2.5 million, and it's up to 5 years. There's the synergy grant, which it's a combined work. It combines 2 to 4 PIs with complementary experience. It goes up to 10 million, and it's for 6 years. There will be the announcement of a new grant, where I don't have yet all the details. This is coming. What unofficially we have heard is that will be from 0 to any year after the PhD. It will be up to 12 million, and it will last for 7 years. I don't know the name of this new grant. And there is also the proof of concept, which it's only for ERC grantees. It's about 150,000, and it lasts for 18 months. The only comment extra is that this will change a little bit. The eligibility windows will be changed, will be shifted a little bit. So next, after the 2027, is expected that the starting grant eligibility window will be from 0 to 10 years after the PhD, and the consolidator grant will be from 5 to 15 years after the PhD. So there will be an overlap, and someone has to think wisely for which grant he wants to apply, because he can apply only to one of them at the same year. Now, the fields that, as I say, ERC covers all fields of science. There are no predetermined fields. There are fields for life sciences, fields for physics, physical sciences and engineering, and social sciences and humanities. There are 28 panels in total. Most of you, I guess, in high energy physics, you will either go for this one, the P2, where I am also working for this, and or maybe P1. Now, all these panels, the 28 evaluation panels, are the ones that evaluate the proposals. Each of these panels has 16 to 18 scientists across all disciplines and countries. And what I want you to remember is that in these panels, 1, maximum 2 people will be close to your field. All the rest will be like generalists. And I will comment again to this, but when you write a proposal, that's a very, very important thing to remember. Well, as I say, I will come back. And all these scientists are renewed regularly. So remember this, the generalist thing. Now the application process. So why, first of all, to apply for an ERC grant? So ERC offers independence, recognition, and visibility. The research topic is of your own choice with the team that you will build by yourself. And only in Synergy, there are 2 to 4 principal investigators, as I have already mentioned. There is a true financial autonomy for 5 years. Synergy is 6 years. You can negotiate with the host institution the best conditions of work. You can attract top scientists, top members for your team, and also collaborate with top scientists. The grantees can move within Europe even the next day of the grant. So this gives you a lot of power to negotiate, as I say here, for the best conditions of work. So, for example, you get a grant with a host institution A, you sign, next morning you can move to host institution B, and ERC has no problem at all with that. And it attracts additional funding. Also, you can apply from everywhere in the world. There are opportunities for researchers outside European Union to come to Europe, in a sense. So there is an additional 1 million for these grants if you are outside Europe and you want to move to Europe. Also, grantees can still keep the affiliation outside Europe of the home institution. The only constraint, let's say, is that they have to spend at least 50% of their time in Europe. And even 10 team members might, or partner organizations can also be based outside Europe. So if you have an original idea, curiosity-driven, if you want to lead your own research team, I advise you to apply. Now, some comments, some hints about. So let me explain a little bit how it goes, the application process, and some hints on that. So, first of all, you have your idea. You decide to apply for an ERC. First, you have to choose your panel. As I mentioned, there are 28 available panels, and you should go for one. But there is a possibility also to request a review also from a second panel. So as I say, I mean, you can be in high energy physics, string theory, you can be a mathematically focused project, and you can apply to physics, but also to mathematics. But also there can be the proposal can be transferred from panel to panel. Now here, comment. It's not necessary to choose a panel based on the number of grants funded. This could look like, you know, this panel funds more grants, so maybe you have better success rate. No, that's not true. The success rate for all panels is the same. I will come back to that also. Next, you have to write your proposal. The key points to stress is your proposal truly innovative? Does it go beyond the state of the art? What is the success expected despite the risks? And is it feasible with the available resources and time given? You remember, it's 5 years, the time usually. Now, when you write the proposal, you should keep in mind these two things. First of all, your proposal has to excite at least one panel member to fight for your proposal. And the second thing is that it should be in such a way written that should be understandable and interesting also for generalists, because as I say, most of the people who will receive your proposal will be journalists. Maybe they don't have an idea of what you are talking about, but they have to understand and to feel that it's an important research that what you propose, and believe that you need to be funded. Finally, there is a second stage. I will explain all this in more details. There's a second stage that you have also to convince the lead reviewers of the field. Now, the application structure goes as follows. If you open basically the manual, you will see that there is a part A, which is our general information. Now, there are two important parts. B1, it's the scientific information, some general stuff, but the key points are here and also here. So the B1 contains a scientific synopsis, so a short version of your proposal. This part here, there is you have to write about yourself, the CV and your track record, and then there is a part B, which is the full proposal, the full text. Now, a few comments about the CV. As I say, the ERC is based on the excellence of the project. So for the CV, what your CV part should do is to prove that you can achieve the goals of the proposal. Metrics like age factors, age indices, and or high publications in high impact journals are good, but are not a criterion. So, of course, have to be mentioned, but this is not the criterion for the ERC. Of course, publishing also primarily with senior scientists, etc., sometimes give rise of concerns about your maturity and independence. Now, the synopsis. The synopsis, as I said, is a short version of your proposal. But this is the part that will take you from step 1 to step 2. I will come soon to that. So the scientific synopsis is super important. As I say, it should be well written. Avoid jargons, excessive highlights, or sloppy manuscript, and do not oversell yourself. That starts to piss off sometimes reviewers. Remember that you are talking to scientists. Make it accessible as possible to generalists. And also give it for a proofread to multiple people. And then the full proposal. The full proposal is the part B. Is in part B. If you manage to pass in the step 2, then this part will be accessible to the panels. Try to clearly link B1 and B2, those two, the synopsis and this full, but don't repeat yourself. Here you have to present methodology, work plan, mitigation strategies. In synopsis, you just have to mention. Here you have to really describe them. And try to be as quantitative and qualitative you can. So about the budget, finally, this is a fast comment, actually. You have to give a budget analysis. The point of the budget is just that it should be well justified. If it's well justified, then you might get it. So the panels do not micromanage. So I remember once the ERC president was saying in one of the briefings that if, for example, there's a proposal that asks for a Ferrari and well justify the Ferrari, then he will get it. And finally, ask for funding for open access, which is obligatory for the Horizon Europe. Now, what is after you submit? What happens? The evaluation process goes in 2 steps: step 1 and step 2. Step 1. All projects will be distributed to panel members. Typically, 4 of the panels will read your proposal. Typically, 4 of your panels will read your proposal remotely. And then they have access only to the synopsis and your CV, what I was saying, the B1 part. Then there is, sometimes of course there are because there might be they might be necessary that there is no speciality for a field from that panel, and maybe they can be asked from another panel. But typically, the 4 people will get your proposal. And as I say, most time 1 is their specialty. The other 3 can be close or generalists. Then, after this part, this remote assessment, there's a panel meeting. Everybody, all the panel is meeting in a room, and then they discuss each proposal separately, and then they give a rank, A, for sufficient quality to pass to step 2, B, high quality but not sufficient to pass to step 2, and C, not sufficient quality to pass to step 2. However, if there was an infinite budget, then all A's would somehow pass to step 2 with a good hope. But also because of the not infinite amount of money and not infinite time of the panel members, only the point is that out of these A's, only 44 can pass to step 2. So the A's are ranked, and only the top 44 will pass to step 2. There is a list of A, not invited projects that they have they are of high quality, but they will not go to the next step. Therefore, from step 1, 44 maximum go to step 2. Then there's again a remote assessment of the panel members, but now to the full proposal. Now the proposal is open fully to the reviewers. They can read everything, B1 and B2. But also, apart from the panel members, it's asked the assistance of the remote reviewers. Remote reviewers are specialists on the field. There can be 4, minimum 4, up to 8, 10. It doesn't matter. But there is a number of reviewers. And then, after this remote assessment, there is a panel meeting again. Only the remote reviewers, they have just to send their assessment. The panel members will be present in this panel meeting. And in this panel meeting, all of those proposals will pass an interview. The PIs pass this interview. Usually the interview is typically of 25 minutes, but how it is distributed, how much time the person has to present. So it's maybe 10 minutes and 15 minutes questions or different. This is something that is adjusted per panel. And then after this, there are proposals funded if within available budget and proposals rejected at stage 2. So if you want the idea, the overview of this funding process is as follows. So imagine that all these are the projects. So there are projects C that they got C, the project that they got B, and there are projects that they got A. Now all these projects up to the 44 can go to step 1. Step 2, sorry. These, therefore, are the A is non-invited. And from this 44, the line of the budget limit, so these ones will be funded, is defined by the limit of the money that we have. What is a key point here to stress is that the success rate across all panels is the same. So if you have, for example, 200 applications, and let's say the success rate is 10%, then more or less 20 will get funded. If you have, if in another panel you have 10 applications, then 1 will be funded. Still 10% will be the success rate. So it doesn't matter if, of course, because the point is that if there are 200 applications, then you have to fight against 200 well-written proposals to be on this top. So the point is that the success rate is the same. Now, after a few months, actually, there can be more budget, and they can usually there are 2, 3, sometimes 4 more projects to be funded from those. So, it's still there is a short list, and you can get funded. And finally, feedback is sent to all proposals. Now, there are some limitations. Yes. Depends on the application on the grant. So, for example, in the starting grant last year, it was 180. In consolidator it was 130, and in advanced it was something like 100. But I will come to that. So, but there are some limitations also. These numbers A, B, A's, and so on have some impact on your application. So, if you are A, independently, if you pass to the step 2 or not, still your quality is very high. Okay, your quality is very high, so you will be in the, let's say, then A's can reapply next year. The B's has to wait for 1 year, and the C's has to wait for 2 years. Okay, I have to run. So some hints now when you prepare your interview. First of all, try to have clear slides. Focus on science. You don't give a talk to business. This is not a business presentation. You talk to scientists, and sometimes things that you that you hear from YouTube, for example, they don't work in these panels. Keep the time. Be ready for questions that you don't know the answer. Be fair, and also try to be short and on the point. Focus on the method, know the methods and the research area well, know what your competitors and collaborators are doing. And if you have done something, present it. Now, some typical reasons why you might be rejected. So first is the scope is too narrow or too broad. It's unfocused. There is no clear groundbreaking aspect. The work plan is unclear, or there is no sufficient risk management, or your methodology is not very clear. About the principal investigator, you have insufficient track record, or it's not clear if you can carry on this project. But what is important to mention is that even if you fail, don't lose hope. Read the feedback from the reports, because as I say, after the evaluation, you get a report. Try to answer these questions and reapply. There is a very high success rate for applications which have been reapplied. And finally, the epilogue, these are the dates. Now I'm out of time, so these are the dates. You will have these slides and you can access them. For the starting grant is 14th of October, Synergy 5 of November. So these are coming soon, Consolidator 13th of January, and so on. This slide just shows what is the increase of number of applications in the starting and consolidator. So this is the increased number. So the 6% is increased. Now it's 14% increase between 2022 to 2023. So there are more and more applications. So last year starting was 180. We're expecting 220 maybe next year. And these are some numbers about the ERC. And thank you. Yeah.
For the nice presentation, we can move to the presentation of Alessandro, and we will get some time for questions at the end when there is during the discussion. Okay.
Thank you. Can you hear me? Yeah, sounds like, right? All right. Thank you very much. So I would like to tell you something about a rather different scheme, which is the cost scheme. It is quite different from the ERC because it funds network grants and the rules are quite peculiar. So the cost director yesterday said something about it, but I'm going to very briefly repeat some of the main points and give you some other information. So cost funds networks, and these networks last for 4 years. The way that this funding is structured is that you get an amount for direct costs, so that's money that you can actually spend for your scientific activities of the network, plus a 15% of overhead costs that go to the institution that manages the grant. This is important because this number is actually relatively low. It's quite a bit lower, for instance, than for ERC grants. And I will come back to this in a moment. The amount that you get will depend on the size of your network. And the first year is fixed. I think currently something like 135,000 euros for the first year. And then it can grow if your network grows up to a maximum which is around 250,000 euros per year. Plus, there can be some little adjustments. There can be a little bit of extra money that you can get if the stars align correctly. And even if it is a network grant, it is not like other type of grants where there are different beneficiaries. So there is only one host institution that hosts all this money and does all the work. If you think about our cost network, many of you are seeing Elvira for your reimbursement. This means that the University of Padova manages the reimbursement of all the people that attend this meeting in Stockholm and the people that attend meetings in Athens and everywhere else. And if a person uses the money of this network to travel from Paris to London, it is Padova that pays for it. That means that it's actually a grant that comes with a lot of administrative work. And that means that this amount of overhead actually is really needed in order to pay for the administrators that do this work. And you can expect that some university will say, we don't want this grant. It's too much work for the money that the university gets. If you have to put a person part-time to do the reimbursement, to do the paperwork, this 15% will not cover it. So that's something to bear in mind. What can you do with this money? Well, if you are in the network, if you are in this conference, you probably have some idea. You can use it to fund or co-fund conferences such as this one, or such as the targeted meetings that we had throughout the year. Maybe some of you went to Sofia or to Athens to some of our meetings. And you can use it to support academic exchanges, our short-term scientific missions. These are point-to-point travels for people in the network that want to carry out a project, a fraction of a project somewhere else for a few weeks, and we can give money for that. For instance, this year we gave around 60,000 euros to people that these sort of academic visits. On top of that, there are conference grants, and these are grants where somebody from the network wants to present their result at some other conference not organized by us. So for instance, you want to present your results at the string math conference, the string conference, what have you, and you would like to go, you have a chance to present, but there is an issue with the money because you don't have the money to travel to wherever the conference is, and we can help with that. The network takes place around the coast countries, which are sort of Europe plus. So you can see them here, they are the colored countries here. And of course, they involve the European Union, but actually several other countries. They are divided in 3 categories, and the most important categories are the purple countries, which are essentially the main regular countries of this network, which are among also the funding ones, and the one in green, that are countries that have full rights under cost. They can take all the benefits, but according to some indicator, they are considered as developing under the profile of research. Because of that, cost has a large emphasis which actually comes from the European Commission, as you have heard from the director, in funding these specific countries. So it's important that your network, your participants are based also in these countries, and in fact there are some thresholds. Israel here in orange is a cooperating member, it has a bit of a special status, but you can fund participants also in Israel currently. The cost action is not run by a principal investigator like some other projects, it's run by essentially a committee, the Action Management Committee. And formally this committee is made of people appointed by their governments. So all the people in our management committee have been appointed by their government. In practice, this means that there is some office, maybe the Ministry of Research or some funding agency that is in charge of vetting the people that are on this committee. And this has the final decision, but it's a very large body because an action with 20 member or 25 member states would have 50 people in the management committee. So it's not very easy to run each and every decision by the management committee. There is a smaller action core group, which is a little bit smaller and takes care of the day-to-day running of the action. How do you apply for cost? And this is where the surprise probably will lay for you. Well, you need a network of proposers. So this is a bunch of people that say, we are interested in running this network, and this network has to be sufficiently large to make it believable that you have enough people to actually staff the network and run the activities that you are proposing. It has to pass some threshold. There is a numerical threshold. At least 50% of the country involved should be ITCs. These are these developing countries, so to say. So for each, if you have France, you also have to have another, maybe Portugal. If you have Italy, you have to have maybe Bulgaria and so on. So you have to be very careful how you balance. There is also a criterion of gender and diversity and age diversity. So you don't want to have people of only one gender or only senior or only junior people. But this is not a strict criteria. There are not thresholds here. The application is actually quite easy because it's about 12 pages, including tables, diagrams, and whatnot. And a large part of it is essentially scene setting. It's read basically by a completely generalist audience. So you have to first give a bit of context, then you have to explain what you do, and these 12 pages go by very easily. One thing that is very strange, and I don't think most of us are used to it, is that the application is completely anonymous. In fact, it's explicitly forbidden to say things like our network of proposer involves the dean of the university so-and-so, or it involves the 3 people that won the ERC grant. You cannot give any hints that would allow to pinpoint who are the people involved in the application. If the proposal is successful, the proposal, in particular this technical annex where the description is, becomes the memorandum of understanding, so it becomes the blueprint for the action, and the network of proposers, if they want, become members of this management committee or the core group. So now we come to a personal appeal from me to you. This network, I think, is important. I think it helps our field, and our network, Theory Challenges, the one that is funding this meeting, is almost finished. I'm exaggerating a little bit. We are finishing our 2nd year out of 4, but bear in mind that when you apply, it takes roughly 1 year from when you submit the application to when you start implementing the project. So if you apply now and you are successful, there is a deadline at 21st of October, your project will start next November. So there is a bit of a delay, and it's good to start thinking about applying already now. One of the most difficult things that I did when I was trying to put together the application was to put together this network of proposers, these colleagues from several countries that do relevant things. This was very time consuming, but thankfully we already have a network, and you can look within our membership for this network of proposers if you're interested in applying. And when I say apply, I don't say necessarily apply to make a string theory or a Eurostring network. If you think that your field has a story to tell and needs a network, it could be for some other subfields, maybe more centered on supergravity, more centered on gauge theories, integrability. aspects of mathematical physics, relation to geometry, to pure mathematics, and so on. And the network of proposers can involve people of any seniority, including postdocs, in principle even PhD students, but at least the people leading the network should be, I would say, faculty or junior faculty, because at some point you will have to implement this decision, you will have to talk to your university, set up the network, and a little bit of stability is needed for that. Okay, this is all that I wanted to say about the cost network. I have some more general comments about grants and so on. I reserve them for the discussion. So for now, thank you very much.
Thank you very much. So now I would invite all the panelists to take a seat and we can start with the discussion. The discussion also involves the public. So if you have comments or questions, please feel free to raise your hand and step in into the discussion. We will have our valid helpers taking charge of the questions and the comments.
Okay, let's go ahead. Hello, everybody. My name is Oliver Schlotterer. I'm at Uppsala University. And yeah, I was told to share some anecdotes about ERC applications. So let me start historically. First time I tried was 2015, applying for a starting grant as a fourth-year postdoc, where I failed miserably. And I tried again 2 years later for starting grant, 2017. Then I was more lucky. And believe it or not, I'm so glad that I wrote this unsuccessful application before. Because first time you write such an application, there's a lot of new things to learn. How to present your research in an accessible way to generalists, but also the CV parts. This was quite tricky if you have never done it. And there was so kind support from Max Planck Institute for Gravitational Physics to teach a newbie like me how to write this CV part properly. Okay, so after going through this painful exercise, the first attempt, then later on you can get back to it. I could 2 years later take the failed proposal as a template to see how the CV was filled in. So it's much less work to update such a thing if you had already submitted a complete proposal. And also, there were 2 years in between the two attempts, so a lot of time to meditate about the mistakes I did in the first attempt. You get, of course, new scientific ideas, but also you have a lot of time to contemplate of how to lay out your visions in a, well, proposal-compatible way. But still, there is this frustration factor in the air. You saw it on the slides that only your 5-page synopsis is read and your CV part is read in step 1. They simply trash the 15 pages of main proposal if you don't proceed to step 2. And this is what happened to me the first attempt. Okay, so message to draw from this. Please apply for the different ERC formats well before you're out of the age window. So if there's a cutoff 7 years after PhD, think seriously about it in your 4.5th postdoc year, such that you have a second chance. Keep in mind, you may not be able to apply again in the next year, depending on the grade you get. Okay, so this was starting grant experience. Then in 2023, I applied for a consolidator grant and again failed miserably. And I'm quite glad about that, because otherwise I could not have applied for ERC Synergy, which was in fall 2023. I guess the local Uppsala colleagues in the room might remember how stressed out I was in that period. So this was a Synergy grant proposal together with Ruth Brito from Trinity College Dublin, expert in QFT amplitudes, with Francis Brown, mathematician in Oxford, number theory / algebraic geometry, with Axel Kleinschmidt, string theorist, very experienced in perturbative and non-perturbative aspects, how they go together, and automorphic properties with a very mathematical leg. And yeah, myself identifying as a string amplitudiologist. Yeah, so the 4 of us wrote the Synergy proposal together, and there was a small number of joint papers, but we mostly knew each other well through conferences and through each other's papers. So for instance, many math papers that Francis Brown wrote were absolutely essential for the string amplitudes adventures of Axel and myself. Or also Ruth Brito had intriguing mathematical conjectures in her work on Feynman integrals, some of which were proven by Francis Brown. So we have been in scientific contact in various ways. So that's why we felt it's a very organic and natural choice for the team to apply in. Then evaluation criterion. Now this is special to Synergy. They make it a central evaluation criterion whether the project is such that we would fail individually. Is the project exciting enough such that if the PIs were to apply individually, that they would fail by lack of expertise? So this means in writing the proposal, you have to constantly walk the line to be on the one side, self-assured, yeah, we have a good track record, we can do this, but still make it clear the project is super ambitious and we need each other's help. It should become manifest that you wouldn't get away with 4 consolidator grants, for instance. Yeah, so this walking the line is quite tricky in preparing the proposal. And yeah, the synergy aspect is really important. One hears of cases where top-notch scientists apply together for synergy and don't get it because there is some complaint about lack of synergy. So really think about explaining the project and explaining the synergy aspects as clearly as you could possibly do this. And so in our case, for instance, out of the 11 referee reports, there existed complaints why we didn't invite, say, a phenomenologist or an experimentalist. So just to give you a scale, even if you have this bandwidth between pure mathematics and quantum field theory amplitude experts, there will still be a referee who complains that the consortium could have been even broader. Yeah, then concerning the evaluation process, there are 3 steps in the Synergy grant evaluation, and step 1 doesn't have these different panels. Instead, there is a big pool of generalists reading your proposal. So this 5-page synopsis for a Synergy grant proposal has to be extraordinarily widely accessible. So you read it, avoid jargon, and for Synergy, it kills you even more if you have a trace of jargon. So in preparing the synopsis, even more care is needed that this is accessible to a generalist. Okay, maybe I close with some concrete advice to those who consider applying for ERC Synergy grant. So choose your team wisely. You have to walk the line between, well, it should be broad, it should be an exciting project that can only be done by a team. But okay, maybe don't go too far away from one another because they still want to see a bit of coherence, of course. And start with the project planning quite early and also start the writing process early on. It was really valuable for us to get together in person for a weekend. This was maybe 5 weeks away from the deadline, and we should have done this way earlier. Because when you're sitting together in the same seminar room and you do some writing of the abstract, the first pages of synopsis, then you see, okay, what are the little traps? So these are conversations that you can only have if you're together for multiple hours or ideally several days. Yeah, and once you have a beta version of your 5-page synopsis, get feedback, of course, ask all kinds of colleagues, ideally from different fields. Yeah, I mean, different critical friends will have different advice for you. And yeah, also for the interview preparation. Once you are through the 2nd step out of the 3 steps of evaluation, you get the interview invitation and make sure you do a lot of mock interviews. Meet a couple of colleagues you trust on Zoom and ask them to really trash your proposal if they can, to come up with nasty questions. And that's extremely helpful to hear these types of questions from a multitude of different friendly colleagues. And yeah, finally, one can reapply at least if one doesn't get the worst grade in the first step of the evaluation process. Keep in mind that reapplications have a decent success rate, and maybe it pays off to talk to your team early on whether everybody can see themselves on board for a second attempt, should this be necessary. Okay, that's everything I wanted to share for now.
Yeah, sure. So I'm Yolanda Lozano from the University of Oviedo. I was the vice chair of a cost action that was running from 2013 to 2017. The String Theory Universe, it was called. So the rules back then, this was under Horizon 2020, not under Horizon Europe. So the rules changed quite a bit. Finding the composition of the team was not as hard as what Alessandro was mentioning, because there was no rule about the ITC countries and so. So also the motivation that we had at the time was, as you were mentioning, Michele, these are difficult times for string theory right now, because there are once this cost action is finished, we will not have any funding scheme. And back then, the problem was that the field had enjoyed two very successful RTN networks that were funding postdoc positions, they were funding conferences, meetings, everything, but they involved a lot of money. Basically, all institutes working in string theory participated in one or the other RTN network. And when they finished, I think this was like around 2008 or 2009, there was a gap of years in which there was no money for postdocs, there was no money for organizing conferences or anything. We had not heard about this cost program. Nobody, I think, in the string theory community knew about that. I was quite surprised yesterday in the outreach event when the cost responsible was mentioning that this was in place for I don't know how many years. But okay, we learned about this and we thought, well, okay, this is funding networking and cooperation, but this is good enough in view of the fact that there is nothing else. I have to say that people had been applying for RTN networks, but unsuccessfully. So we had like a feeling that string theory was somehow not very much liked at the level of the European Union. So we decided to apply to this with the aim of having a funding scheme that would fund all research in string theory. It was that would be inclusive, because subdividing in different string theory disciplines would make no sense if nobody had any funding. So we decided to try to apply for a network based on this that would do research in string theory, involving all the research lines in string theory. And the initiative came, in fact, from the senior women in string theory, that back then we were about 30-something. It originated like in one of these old networks. We were 4 women that were contact persons from our own nodes or subnodes. We had already been discussing the very few number of women in the field, and we thought, okay, this cost promotes networking, cooperation, but it also wants to create an inclusive scientific culture. It wants impact not only in science, but also in society. So we thought, okay, if here, besides the main theme, say, of the project, which will be research in string theory, we add also like a secondary goal that would be try to address what's going on in this field, that there are so very few women, and what we could do to try and reverse this situation. So we decided to apply with this main goal, string theory research, but then this secondary goal on trying to improve gender equality. In Horizon 2020, this was quite innovative, I must say. We were a bit ahead of our times because when you would read the strategies in gender, whatever, things were not as explicit as they are now. But, well, we managed at the third attempt to get it approved. And this was running very successfully for these 4 years. Everyone in the community was participating because even though this originated from the women string theorists, of course, we were representing just a few areas of the whole string theory research arena. If it is only in terms of we were representing like 10% of the whole community. But of course, we opened up immediately to the whole community. Everyone participated, and I think it was quite a successful action. And I would like to add that I was reading the differences regarding these gender strategies between Horizon 2020 and Horizon Europe. And I read that there are special actions that they are referred as Score 1 and Score 2, which receive extra funding when Score 1 are actions that have gender equality as the main reason for the action to be, while Score 2 actions have a main theme, but have gender equality as a secondary goal of the proposal, which is very similar to what we did years ago without having that scheme that was not part of Horizon 2020. So maybe this is something that the community could consider because there would be some added value if one incorporated this gender perspective. And also taking into account that in spite of years of efforts trying to address why there are so very few women in the field, I think Agnese will present the data tomorrow. We are improving really very, very slowly. So I think the need of addressing this issue is still there. So I think this is all I wanted to say.
So Pascal, in your presentation, there were 2 details on which I want to zoom in. So the first one concerns the open access. I'm very reluctant to waste taxpayers' money on open access journals. So would it be sufficient if we write something like all results will be published on the archive or something like that? Or do we really have to request money for open access journals or something like that?
Yeah, the point is that there are you understand that ERC covers all scientific fields, so there are others that they really need. So in high energy physics, indeed, this is possible, but
okay. So just stating everything will appear in the archive would be sufficient to tick this box.
I think so. Yes, I think because there is a link in the template that shows that it's open, so the access to.
That's true.
Yeah,
yes.
So.
Yeah, but for that we don't need to budget any. Yeah. Yes, that's true. Yes. Okay. Yeah. Thanks. Yeah, and the other question was there was this striking detail that the success rate is fixed, but not the number of proposals that's granted. So it seems to imply that we, as a community, should spam with applications to increase the success rate. Is this the right conclusion?
Well, if you manage to all collaborate in such a way, yes, because that's the idea. The idea is that you have every year there is an amount, is the budget, and then you see how many applications have been received, and then you divide it to the full number. So yes, but of course you have to know that the ones who will fail will have 2 years. I mean,
Sure.
I mean, they have to wait for 2 years again to come back. But yeah, this makes it even more difficult because you have to send a not so well written application in 2 years. So I mean, this can be 1 year that there is a huge. But to be honest, it's super complicated because that's the ERC starts to has a problem with the number of applications that it receives. So as I say, last year for the starting grant it was 180 applications. So each application is reviewed by 4 panel members. This means that if you do your math, you will see that almost every panel member has to review about 50 applications. So imagine this is 180. So if it goes to 250, then they will have to review 60. I mean, so it starts to get too much, and then solutions have to be found, and ERC is working on that. From 16 they go to 18, but they don't. ERC doesn't want to go further than 18 panel members because then it will be too many for a room to discuss, and it will be a mess. And then there are different ideas who are going on. So yeah, so either split panels or we will see. But the point is that since the number of proposals is increasing, solutions should be found.
I think that, well, one point here, sorry if I can, is that we should write the proposals such that we make the life of the reviewers very easy. So we put all the keywords, we put all the thing. He did a very good job introducing all the evaluation criteria and how you can fail. You can take that as a grocery shop list that you have to tick all the boxes. Please, Alessandro.
A couple of comments. So one, inspired by the last question, is not only important, of course, as a community to be submitting applications, but it's also important to serve in panels and as referees. Now, for the ERC, this doesn't apply quite as much because the panels are selected in a particular way, but for the Marie Curie, for instance, typically panel members are chosen among people that ask to be panel members and put their CVs in the expert portal of the European Union. And starting from a senior postdoc, any of us can do it. I mean, you can always propose yourself, even if you are a junior postdoc. I would imagine that you have to have a little bit of research experience, and you can do that. And I think that's very important because in the very best case scenario, the people that read your application will have a little bit of bias, personal preference for whatever is the field that they think is most exciting, right? And if there are not many people from our field, that's maybe not great. Of course, people tend to avoid this bias, but I think it's a bit normal. People will have more understanding and more enthusiasm about some field. And to be entirely honest, it can even happen that not all panel members are necessarily at the same level of scientific excellence as some other people that maybe don't think it's worth their time. So I would encourage you, both for cost and for Marie Curie and for your national funding association, to consider registering as potential referees, potential panel members. Very often it is actually a paid job. Of course, it's not paid lots of money, but it's a decent amount, much better than refereeing a paper, and not that much more work, by the way. So I think that's something to keep in mind. The other thing is just maybe a comment for Pascal. Honestly, in our field, I sometimes have the feeling that some of us have struggled a bit to find a house or a home in the panels because we are, many of us, in P2, but a little bit more mathematical than most, right? So I do wonder if at some point some panel split could help for people that work in our field at the boundary between mathematics and physics.
yeah, the situation now is that this high energy, let's say, field is the P2, and in this panel there is high energy and low energy physics. So, and of course, it should contain also experimental physicists, theoretical physicists, and so on. So it's natural that some applications about holography, whatever, and it's very, very technical and very mathematical, and panel members have trouble to understand what's written. On the other hand, that's one of the key points of applying. Actually, I have been in this situation for. I mean, I am a string theorist. I was working for 25 years in the field, and I applied several times, and I know how it is. But I think that it's important to remember that you don't. When you apply, you don't write to your colleagues or to your field. You should be expressing yourself wide enough that everybody who knows some physics to be able to understand what you want to do and try to attract their attention.
Can I ask?
Yeah, sorry, hey. I had a question also about the ERC and how the panel works. So just like based on the numbers you gave and extrapolating a bit, it seems that there is like roughly one successful application.
Can you
sorry,
talk a bit
stand up?
higher? Because
sorry.
Yeah.
So there is, like I'm extrapolating a bit the numbers, but it seems that there is like roughly one successful application per panel members in our field, maybe roughly. So it seems that it would be fair, or naively, I would think that everyone just pushes their favorite application and
no,
it's not useful to impress the generalists. Or how much weight, or the question is how much weight the generalists actually have in the final decision.
So the question basically is if every panel member somehow pushes one application. Yeah. It's not. No, it's not. That's not the way. There are cases where, for example, one field doesn't get any applicant which managed to get a grant. So I wouldn't say that. To be honest, panels are very dynamical things. There are people who are much more powerful. Let's say they have high voice. Others who are softer. Yeah, but that's how it is. I mean, how life is. So okay.
But how would you estimate the distribution of weight?
I cannot say, but I don't think. But I wouldn't say that it's one per. So it's not that let's distribute. Let's find our best, our favorite one, and one for the high energy guy, one for the EFT guy, one for the, let's say, neutrino guy, and so on. So it's not. I don't. Yeah, I wouldn't say that's like that. But
okay, thanks.
Okay. I also had a question about the ERCs. So you said that the emphasis is moving a bit from the scientific excellence of the PI to that of the excellence of the PI to that of the proposal itself, which I think is a good thing. If I look at what happened, I felt like pedigree was too important sometimes in awarding a grant from the outside. Of course, I couldn't read all the proposals, so I think it's a good thing. But what does this mean in practice? Is this different guidance for the panels? Is there some change in the forms they have to fill out, or what does this really imply?
Yes, so the panels are informed again and again about, because all these rules are changing. So the council is coming, they are meeting 3-4 times per year, and they discuss about the strategies. The latest is, as I say, that it should be a shift to the proposal, the excellence of the proposal. So if a panel member somehow forgets the rules, then we have to remind that this is not a criterion. So if someone says, okay, this is an excellent PI because he has published so many times in the PRL and the physics, whatever, science and so on. And then we have to come back to him and say, okay, but you remember that it's not a criterion. You have to, or for example, all these things are important. For example, if you have, let's say, 20 PhD students, okay, an army of them running, this is good just to show that you are you have the leadership. You are able to lead a group, which is good for ERC. But up to that, you don't. It's not a criterion. And we come back to them and they say we discuss it and we say, okay, but you have to follow the rules and the criteria of the ERC. Yes, it's happening. And if someone, for example, or even in the reports, we come back and we say, okay, but this was not a criterion. You should.
Yeah, I have a question. So you mentioned that there is a part of the proposal that involves having some more or less clear timeline and mitigation strategies and this type of thing. And I would like to ask, like in our field, like there is a component which is like a bit of serendipity of having a good idea. Is there like what tips maybe would you have to deal with these parts of the proposals?
You had.
Oh yeah, still a technical question. You had on your slides.
Yeah, okay. Yeah, cool, please.
You had on the slides that there's a new possibility to apply for startup help if it's a applicant from outside EU, up to 1 million.
Yes.
Yeah. So
this was always the case.
Okay. Okay.
1 more million, I believe.
1 more million. Yes.
It's now 2 million.
So you get if you are, for example, in starting grant that's supposed to be 1.5, then you can ask for 2.5 because you come from somewhere else.
And now if a panel discusses such a proposal and if they decide to give the startup help, does it mean there will be another proposal that doesn't get funded because
yes.
Okay, I see.
Yes, the point is that because sometimes, there was an attempt that the panels maybe, they should look at the budgets and say, okay, yes, but if we move this guy above and maybe more will be, or ask them to cut. As I say, the panels do not micromanage, so they don't go in very many. I mean, if it's something exaggerated, maybe they can ask for more details, or they can try to figure out if this makes sense. But yes, so the point is that if the first, let's say, 10 has 2.5 million, ask for 2.5 million, then this is 25 million. Okay, so this means that no more can go. So the line is when the money the budget limit is reached. So if the first are very expensive, too bad for the next ones. The ranking is based only on excellence in the project, not the budget. The budget will come after, and if the panel agrees that it makes sense.
Okay, so there won't be any exchange in between the panels to account for the. Okay,
no,
thank you.
They cannot say that. Okay, even if it's 1 million that can be given to a next one and can be in the success field and success list.
Can you also answer the question by Guillermo?
Yes. So what? Okay, can you repeat again because of. Well, to be honest, these parts, the mitigation, the plan. Okay, I am also a string theorist. Okay, so I know that a plan is quite vague. You cannot really say that I will work on this field for 3 months and after I'm mushy. But it's something that the applications want that. So you have to play the game. So that's what I would say. I mean, really, now I am speaking like an applicant. So but you have to have it. Because if you don't, then someone will come and say, yes, but your work plan is not, it doesn't exist, or it's too vague. Even if everybody knows that work plans cannot really be followed, and they are not followed, and actually I am also in the monitoring of the grant. So when you have your grant, I will have to check if what you supposed to. So, but the general approach of the ERC is that we are very relaxed, because we know that, okay, I mean, you say that you will publish 10 papers, you publish 7 papers, okay.
Yeah, I think my advice would be to don't start from scratch, right? Just before you start writing, gather proposals from your friends who got it, who maybe didn't get it, maybe get the feedback, ask around for success, for examples. And then you'll learn these kind of things by example.
I think it's time for coffee. So we can thank the panelists again. And as main take-home messages, apply.
Okay, so welcome back. We need to start immediately here because of the dinners we just heard. So the first speaker of this session is Andrea Day, talking about better alone on the string theory of a single NS5 brain. Please.
Okay, is better now? Okay, so I was saying the main topic will be to present what should lead soon to a very neat example of holography beyond the ADS-CFT paradigm. Okay, let's start. So we are taught that we can understand the duality between ADS5 cross S5 string theory and unequal 4 super Young mills by looking at the decoupling limit of a stack of D3 brains. And something similar can be done for a stack of NS5 brains. And this leads to a duality where the bulk theory is a string theory in a geometry that is asymptotically linear dilaton. It means your dilaton is linear in the radial coordinate. And the dual theory is a 6-dimensional theory, rather mysterious, and the name is known as little string theory. And we'll learn more about this during the talk. So let's look more closer to this, how this decoupling limit works. So you start from a stack of parallel NS5 brains. So you have some flat directions along the brain, and then some harmonic function for the directions perpendicular to it. And you can, if you want to isolate the physics on the brain from what is happening in the bulk, you can you scale to 0 G string and R at the same rate. So technically you replace something like R equal G string times e to the rho. And you take the limit, you end up indeed with a dilaton that is linear in the radial coordinate. And the geometry that you obtain has a flat 6-dimensional Minkowski, a linear dilaton direction, and the 3-sphere that you can model from the worksheet as an SU2 Vezzomino-Witten model. And this subscript 1 means is the supersymmetric one. Okay, what's the problem with this? The problem is that rho, which runs from -infinity to +infinity, is not bounded. So this means that the dilaton is not bounded and your string coupling can explode. So you have a region where perturbative string theory doesn't apply. Okay, how can you solve this? So you can, instead of having the NS5 brains all together parallel, you can distribute them in a circle and repeat a similar decoupling limit where you scale G string and the radius of the circle on which the NS5 brains are distributed at the same rate, keeping alpha prime and the ratio fixed. And this leads to a background where you have some cylinder. So this is again the radial direction. Again, the dilaton grows as you go into the bulk, but it saturates at the tip. And the value of the dilaton at the tip is a modulus of the theory, so you can choose a small value, and then the string coupling can be adjusted to be small everywhere. And in the region closer to the boundary, this looks like a cylinder, and the radius is the string length times the square root of n5, which is the number of how many NS5 brains I have. Okay, and this can also be studied from the perspective of worksheet CFT. And you have the cigar is modeled by this SL2R over U1. Again, is supersymmetric, and the level is equal to how many brains I have. And similarly, the rest of the metric is given by SU2 over U1, and you have some flat directions. So we start from 3 plus 3, 6. You take 2 directions out, so this is a 4-dimensional space, so in total 10 dimensions as usual in string theory. Now, an equivalent formulation, you can re-express this. It's not obvious, but has been checked thoroughly, that an equivalent formulation is having a unique denominator. You have, again, SL2R and SU2, both the supersymmetric version of the Vezzomino-Witten model, and you do some null gauging. Again, you take away 2 U1s. And this will be the protagonist of this talk, and will play mainly with this object. So this is kind of the motivation of why we start with this worksheet CFT. Okay, so this is... Okay, so why this whole is interesting, because the boundary theory that you obtain once you decouple the gravitational degrees of freedom is a 6-dimensional theory without gravity, but it's not a local quantum field theory. So, for example, has some features that are more typical of string theories, like it obeys T-duality, and it has a Hagedorn rate of growth at high energies. And part of the reason why we don't understand much of this theory and we don't have a first principle definition is because it's both strongly coupled. So essentially you have scaled G string to 0. So all the scales that remain in the problem are alpha prime, which is not small a priori, hasn't been scaled at all, and the separation between the branes. So in general, it's a strongly coupled theory. And is non-abelian because they have a large number of branes, so you can have interactions between the different branes. Okay, so how to approach this? One possibility is to think, okay, both difficulties should become much simpler if I have just one brane. So the easiest is, okay, it should be abelian because there are no strings or D branes stretching between different NS5 branes. And the cartoon, this is not really rigorous, but the cartoon that you can sell is that you remember the cylinder that described the throat in the geometry has a radius that scales with square root of n5 times the string length. So when you have n5 equal 1, the throat is of the same size of the string. So essentially the string doesn't fit there, and it means it will not get to approach the strongly coupled region, which is deep in the bulk where the dilaton explodes. So it's a bit of a cartoon, but the intuition is that everything should simplify if you have just one single NS5 brane. Okay, so this intuition is an old one, but the reason why it hasn't been studied for long is because there are technical problems in defining just the theory of one NS5 brane. And that's the goal of the talk. So we want to give today a worksheet definition of string theory for a single NS5 brane and explain how the common law of this not been possible because of well-known technical problems that I'm going to review can be overcome. And ideally, if once we understand this, we will see that this is a free theory with some constraints, so it's amenable to an exact analysis. So one should be able also to study the states that this string theory contains and get to some guess of what the boundary dual should be. So it should be some 6-dimensional supersymmetric abelian theory. And ideally, one can get to an exact solution of the duality because it's a special regime where things should simplify a lot. And this should give something like the analog to the tensionless string, but of ADS3, but in the case of this little string theory holography, where we are a bit lost when the number of branes is a generic number. Today, I will just address the first line. I will try to convince you that we have a string theory that defines rigorously and overcoming these difficulties when you have just one NS5 brane. Okay, so we said that we start from this when the NS5 branes are N5. So the naive guess is, okay, wherever I see N5, I replace 1. Now, the problem with this is that you have the SU2 Vezzomino-Witten model, the supersymmetric one. This you can rewrite into a bosonic contribution that shifts the level down by 2 and free fermions. And the problem is that doing this way, the bosonic part has negative level. So the Vezzo-Minowitten model associated to it is not unitary. And this is the reason why so far we have said, okay, what should I do? This is not a well-defined string theory. It doesn't really make sense to set N5 to 1. Okay, but relatively recent in the history of this NS5 brain problem, we have encountered a similar problem that smells the same and has been solved. So for the tensionless ADS3 cross S3 cross T4 string, again, you have an SL2R factors for ADS3, an SU2 factor for the S3, and then 4 free bosons and 4 free fermions. And again, the problem was that if you really want to insist on N5, the number of NS5 brain in the background being 1, you had the SU2 at level -1. So same problem, it looks like. Oh, this is bad. Very bad. Okay. Let me, it's already the end. Okay. No. Okay, so what was the solution? The solution was to rely, and let me describe first at N5 bigger or equal than 2, you have a map between two different formalisms, the RNS formalism, which is the one we are used to, and the Berkowitz-Vafa-Witten formalism, where you bosonize your free fermions. It's just a bosonization map, so it's not something really mysterious. It's just a redefinition of variables. And you keep the bosonic part. So you have SL2, the supersymmetric, you decouple, you shift the level, you have the bosonic part. Same for SU2. And you have 6 free fermions. You bosonize the free fermions together with the ghosts. And what you obtain is 4 BC systems of dimension 1, 0. So this is just a map that you have at N5 bigger or equal than 2. And in terms of these free fields, you can, in terms of these fields, you can generate PSU112. So the associated superalgebra. So naively, you start from SL2R and SU2, and you replace with a supergroup. This at N5 bigger or equal than 2, when both sides are well defined. Somehow at N5 equal 1, this doesn't really have a meaning, but it does have at N5 equal 1 what is on the right. So PSU112 level 1 is well defined, and this was essentially, in a nutshell, the solution for the tensionless string. Moreover, the PSU112 level 1 has a free field realization, so this means computations are easy. And is given in terms of 1 beta gamma system. For the specialists, this is the beta gamma of Wakimoto-like, and 2 BC systems. And you can generate all the currents in PSU112. Okay, so given this, can we learn how to solve the problem for the single NS5 brain in the little string theory holography that I was describing? We are ready for a refined guess then. We said we cannot really set just N5 equal 1 blindly in the RNS formalism, but we can take the supergroup, so take the tensionless string of Eberhard, Gaberdil, and Goppa-Kumar and quotient that. That should solve the problem. Unfortunately, this doesn't really, and the obstacle is that if you look more close to the currents that you want to gauge, those don't have, you are not able to write them in terms of the free fields or of the generators that are contained in PSU112. So if I have to make an analogy, you know, when you play Scrabble, the game where you have to form words out of letters, you want to write a very long word, but you have only vowels. That's kind of the problem. And let me try to be more precise. So we saw that N5 bigger or equal than 2, you can generate PSU112 in terms of the bosonic algebras and 4 BC systems. But at N5 equal 1, you only have 2 BC systems. And the current that you want to gauge is written in terms, at N5 bigger or equal than 2, is written in terms of the BC systems that you miss. So, okay, what should we do? So the The strategy that we follow is to insist on extending the map between RNS and hybrid formalism. So if you take the bosonic algebra and blindly set N5 equal to 1, you have SL2R at level 3 and SU2 at level -1. We provide a free field realization for these two. So we end up with describing SL2, the bosonic part at level 3 and SU2 at level -1 in terms of 3 beta gamma systems. Of course, this alone cannot solve the problem, because we said the problem of the initial formulation of blindly setting N5 equal to -1 is that the model is not unitary. So yes, you have a map between something non-unitary and something non-unitary. So it's not really on its own a solution. Anyway, you can write down PSU112 at level 1 in terms of 3 beta gamma systems and 4 BC systems. So now you can write your current, but the model is non-unitary. And here comes the solution. So we identify a constraint which is given in terms of the free fields that form these bosonic algebras and in terms of these 4 BC systems that restores unitarity. And also we can show that this new formulation is completely equivalent to the tensionless string. So if you look, for example, at representations, you find the same truncation in the spectrum that kills the continuum, and you find the same null vectors that are responsible for it. So essentially, you reformulate the tensionless string in terms of an enlarged space. You have more than twice many of the fields, but you also have an additional BRST constraints. And in the end, you have the same PSU112 with the advantage that now you have more letters in your alphabet. So you can indeed write the current. Okay, so to recap, the solution is that we adopt an alternative new free field realization of PSU112 level 1 that has an enlarged number of fields and that enjoys a map to RNS. We impose an additional constraints that restores the unitarity of the model. So in a sense, now you can go back through this map and you can see in which sense the RNS formalism at level 1 was sick and which is the cure. And we prove that our formulation is completely equivalent to the previous one if you use PSU112 for the tensionless string. So this defines a worksheet formulation of the single NS5 brain string theory in terms of a free field worksheet CFT, those that generate PSU112 level 1, and in terms of 3 BRST constraints, and we show that they are mutually compatible, meaning the total BRST charge squares to 0, so we can impose all of them one after the other. And these 3 BRST constraints are the usual one we are used to, that decouples 2 directions that any string theory has. An additional one that comes from the fact that we are gauging something in the denominator, so it's the null gauging BRST operator. And finally, the one which is special to N5 equal 1, and that restores the unitarity. Okay, so now there are many open future directions that we would like to explore. We just have defined the string theory. So we haven't yet studied what is the spectrum, what it contains. So you would expect the first exercise, you would expect, for example, to recover a number of supercharges that is expected from the boundary theory. So you want to recover something like n equal 2 super Poincare. And on top of that, it should also contain some fields. And the natural expectation is that the dual is some 5+1 dimensional abelian gauge theory, and that this should be identified by studying the BRST cohomology. It would also be very interesting to study correlation functions. So we know that the correlation functions of the tensionless string localize, meaning all the physics is concentrated to the boundary. And holographically, the radial coordinate in the bulk is the one that drives the RG flow of the boundary. So the fact that the theory you are quotienting sits always at the boundary suggests that the boundary theory doesn't flow, but is always the IR solution. So the natural expectation is that you get the IR limit of little string theory, which is indeed a QFT. So something like n equal to 2 Maxwell or the abelian 2,0 6D superconformal field theory, according to the chirality. And finally, you can change the embedding of the currents you're gauging. So in this whole story, the R15 was a spectator, but you can bring two directions of the R15 in the numerator, so that your U1s are linear combinations of the cartans of SL2, of SU2, and also the two extra U1s. And this describes a background that interpolates between ADS3 and asymptotically linear dilaton, and that is naturally believed to be dual to the single trace TT bar deformed symmetric orbifold. So even if we solve this problem, there is also more interesting setups to extend to. So this is all I wanted to say. And thank you very much for your attentions. We learned that NS5 brains are better alone, but physicists are not. So please make my week very strongly coupled and non-abelian. Thank you very much.
A clarification. So you said, if I understood correctly, that this free field realization of PSU 1,1 /2 level 1 in terms of one beta gamma system and 2BC system. So you said that doesn't have the U1s for the gauging, but I suppose you meant they're just not convenient in that formally, because of course it has all the U1, they're just cartans, right? It has everything.
You're right. I was hiding details in the So the currents you're gauging, they are supersymmetric. So you have the current you're gauging is something like the cartan of SL2 plus the cartan of SU2. And of course, you're right. Those you have, because you have a realization of the superalgebra, you know how to write them. But you also have to gauge a fermionic superpartner of this. This comes from the RNS formulation, where you don't want to break the supersymmetry on the worksheet. So you also have to gauge something that is like the fermion dual to J3, so something like Psi3 plus the fermion, which is the superpartner of K3. And what you actually are not able to write is the sum of the fermions times the associated ghost. You're right, this detail was hidden.
And as a small follow-up, is there something like a marginal direction Ramon flux that you can turn on in this story, or it doesn't exist?
Okay, so that's a longer story. I think the most interesting thing is that if you look at the PSU 112 Vezzumino-Witten model, and you rewrite in RNS variables, so you find the SU2 Vezzumino-Witten model, the SL2, free fermions, but not just that. You also have an extra piece that looks like a Ramond-Ramond deformation. So the equivalence is not complete, except when you look at the N5 = 1, what we argue also in the paper is that the modes that are inside this free field realization don't care of this extra piece. So this extra piece is proportional to the constraint that imposes unitarity. So once the fields that survive this constraint don't see that extra piece in the Lagrangian that would erect an RR wall close to the boundary. So at least at N5 = 1, despite the initial Lagrangian is different, for all the practicalities, it is as if that Ramond-Ramond field is not there.
Oh, okay. Can I ask, or is someone? Okay. You mentioned this unitarity problem in the SU2. Yeah. Now, the way you presented it, it was sort of after decoupling the three free fermions from the SU2.
Yes.
But as I'm sure you know, the original supersymmetric SU2 model is not that. And then there's this nice paper of Paolo De Vecchia and Kniznik who showed that you can write it like this. Now, is the original model also, is a full model non-unitary as well?
So if I understand correctly, the original definition of the supersymmetric Vezzo-Minowitten model is that you take the bosonic one where you had G minus 1 dG and you replace with a supersymmetric G, okay?
Exactly. Yeah.
And you just expand. And my understanding is that if you do that, you find the bosonic plus the free fermions.
No, you have to do a field redefinition. This is what De Vecchia and others taught us.
Okay.
In order to get the three. I just wonder, because you do all these translation of variables, if somehow it's related to the same thing that they were doing.
Okay, I'm not sure I understand. Maybe we can discuss later, but this translation is really nothing mysterious. It's just taking your 10 free fermions, you bosonizing 5 bosons, and then you write the new variables are exponential of the sum of these 5 bosons with different choices of plus and minus ones. So it's not something suspicious about.
I'm not, okay.
Okay, maybe we can discuss more. I'm not sure I fully understand the question, or I know the paper you refer to.
Just maybe conceptual question, not technical. So how you motivated this SU2 over U1 times SL2 over U1? You said, let's distribute the NS5 branes. That's fine, but that requires many NS5 branes. And then suddenly you jump back to NS5-1. So what's the logic? And also you probably missed the dilaton in this case that has 2 contributions, logarithm of cosh and logarithm of cos of sigma. You have sigma and rho, right? Yeah, anyway, could you again explain the logic? So the outcome, you can postulate whatever you want, but why it has to do with NS5 equal 1? That's the question.
Okay, so you mean, okay, I see. So you're saying you have already decoupled, and that formulation is only for N5. I understand. Yes, I mean, I don't have another place to start from. I think it's natural to look at that N5 equal 1 limit, but I agree that I start from a situation where it's already decoupled. On the other hand, I don't have another worksheet model to start from. So, I mean, this doesn't make obvious that the dual is what we claim. I think one can now just look at the field content. It's certainly a well-defined string theory. To fully sustain my claim, I should show what is the spectrum and show that I recover the 2,0 6D abelian theory. That would probably convince you. I agree. There is not all the evidence yet. Thank you.
We will talk about monographic sum coefficient KM at conditions of black hole.
Thank you. Is it on? Yeah. Okay, let me start by picking this. Let me start by thanking the organizers for having me and for putting the event together. I will talk about 2-point functions at finite temperature in holographic conformal field theories. And this is based on two papers with two great collaborators, Ivan Gusev and Andrei Parnacha. Good. So let me start with some general motivation why to study conformal field theory at finite temperature. And there are various reasons, starting from experimental ones, that quantum critical points in laboratory are always measured at finite temperature. But there are also plenty of good theoretical reasons. And they are starting to be more and more explored. And one of very interesting directions, I think, is that high temperature correlation functions control heavy sectors of CFT. So density of states at large delta and also peak coefficients. And this generalizes formulas such as Carty's formula for density of states to higher dimensions. There are also some ideas how to formulate numerical bootstrap with thermal correlators, and
These, I think, are also very interesting. And all this is part of maybe a general program of studying CFTs at different geometries, and then trying to formulate some crossing symmetry constraints involving correlators on various geometries. When the theory is holographic, then there is also a little bit different flavor, because these thermal correlation functions should be related to black holes somehow. And in this talk, this will indeed be the main topic, how thermal two-point functions are related to fields on certain black holes. Okay, so let me describe the setup and formulate the problem that I want to solve. So among various thermal geometries, we'll look at the most standard one, where I have the thermal circle times the flat space, and beta is the inverse temperature, and we'll stick to 4 dimensions in this talk. And the observable that we focus on is the two-point function of a scalar operator, G beta, and I will also, to make things simple, put the two scalars at the same spatial point, so they will only differ in their Euclidean time coordinate. And then this two-point function only depends on a single variable, and it is an interesting correlator because it satisfies two properties. One is the conformal block decomposition, which in this configuration is very simple. It's just the decomposition in powers of tau, and these coefficients A are called the thermal coefficients, and they're the dynamical coefficients that characterize this two-point function. On the other hand, as in any quantum field theory at finite temperature, this is periodic in Euclidean time. So this is called the Kuba-Martin-Schwinger condition, KMS. And now you see that blocks individually are not periodic. So imposing this periodicity on the correlator gives you some rules on the thermal coefficients. And this logic sometimes goes under the name of thermal bootstrap and has been explored with good success in these works by Iliescu et al. And Marchetto et al. And mostly in the context of Ising and ON models in 3D. And there is pretty good agreement between these bootstrap results for thermal coefficients and, for example, Monte Carlo results. Today I want to look at a different type of theory. So I want to look at a holographic CFT, and let's say an operational definition for this talk of what I mean by holographic is the following. So I'll look at the two-point function of some scalar, which you should think about as a single trace operator. And then I postulate that the OP contains 3 types of operators: the identity, then a tower of double trace operators, and what I will call a multi-stress tensor. So these are composites of the stress tensor. And the scaling dimensions, and you can argue that indeed in large N gauge theories, conformal gauge theories, these are the only contributions at leading order. And the scaling dimensions at leading order of double traces are 2 delta phi plus 2m, and of stress tensors are of the form 4n. And then there are 1/n corrections, but in this talk I will just assume that these are exact. It turns out that the thermal coefficients for the stress tensor sector, so the stress tensor and all the composites, are very well understood, and I will review this from the work of Fitzpatrick and Huang. And the aim of today is then to determine the thermal coefficients of these double trace operators and thereby determine the whole two-point function. Okay, so this is the plan. I will first review this analysis of the stress tensor sector, which proceeds by solving some differential equation in the bulk. Then I will describe how these KMS sum rules can be used to, from the stress tensor coefficients, determine double trace coefficients. And then I will show some results of this procedure and conclude with some future directions. Of course, interrupt me if you have any questions. About the stress tensor, how are these coefficients computed? one looks at the Klein-Gordon equation in the planar ADS-Schwarzschild background. So this is the metric where mu is related to the temperature. And then if you write the Klein-Gordon equation on this background, these authors noticed that if you make the ansatz of this form, this is closed under the action of the Laplacian. So these rho, r, and w are some new coordinates. And what is important is that rho going to infinity is the boundary. So this is kind of a near boundary expansion. But this function shouldn't be thought of as the full two-point function when you push it to the boundary, but only the stress tensor part of the two-point function. And indeed, if you expand this ansatz, if you take this ansatz and push it to the boundary, you will only find stress tensor blocks in the corresponding two-point function. So you can compute these coefficients ijk by acting with a Laplace operator. This gives you some equations for these coefficients. And they can be computed to pretty high order. For purposes of this talk, I should say that we needed to extend this, to rewrite this as some kind of recursion relations, which are familiar from Casimir equations in conformal field theory, but it's a technical point. Okay, so you can actually go beyond this. So the problem with this ansatz is somehow that it doesn't take into account conditions at the horizon. So you can numerically try to solve the Laplace equation where you impose both sets of boundary conditions. And this was done actually in the paper by Parisini, Skenderis, Withers. But it's a very difficult numerical problem. It's a partial differential equation in 3 variables. And the precision that you can achieve is not great. So using this method, you can determine the first, well, they determine the first double trace thermal coefficient. And maybe you can push it to the second or the third, but let's say if I want a 10th double trace coefficient, there is no hope using these numerics to determine. Okay, so we will approach this problem by field theory methods, but let me also, before going there, just mention that if you analyze these coefficients of the stress tensor sector, I will call them lambda n. If you just compute a lot of them and see how they behave for large n, then they have this exponential growth, -4 to the n, and then some power. And if you sum this up with conformal blocks, you will find out singularities in the complex tau plane. And these are called bouncing singularities by some analogy with bouncing geodesics in the bulk. But what is important in the full correlator, so in the full two-point function, these singularities should not be there based on some very generic quantum field theory arguments. So somehow these double traces are also needed to cure these singularities in the full two-point function. Okay. So let me then describe the method and the results. So in order to write down a system of some rules starting from the KMS, for example, you can take derivatives at the crossing symmetric point. Odd derivatives should be 0. So each of these, for each k here, you get a linear equation. So this gives you an infinite system of linear equations which involve the thermal coefficients. And I have separated them. So this is specifically in the case that I have this holographic spectrum. I have separated them so that I view this system as a system for double traces where I know the lambda n's. I should say in this form, these equations were written in this paper. And okay, I will, for convenience, just rescale the double trace coefficients in some way. So now you can look at this infinite system of equations and look at its structural properties. And in particular, there are two interesting observations. The matrix, when you write it in a matrix form, is upper triangular, which means that you can solve it efficiently, the system, by backtrick substitution. But it's also a Toplitz matrix, which means that it's sort of self-similar. If I start looking from here, it looks the same as the full thing. So if I solve for the first coefficient, A1, then I have solved for all other coefficients. I just need to shift some index. So this is, in any case, if you go through this procedure, this is a formal solution. AM is an infinite sum, and these Fs are just what was on the right-hand side. So they are combinations of these gamma functions and then the stress tensor coefficients. So indeed, you see this M only shifts these Fs here. So this is a formal solution because it's an infinite sum, and you should worry whether it's convergent. And in fact, even for the generalized free field, this sum is actually not convergent. So you need to resum it somehow, and I won't go into the details, but what you should do is Borel resum this. So you essentially take this expression, and the Borel resummation is captured by these steps. I'm dividing by 2k factorial. I have some Borel variable, and then I'm taking the inverse Borel transform. So this is the formula that we propose should be used, and I will be somehow using this formula for the rest of the talk. So let's do some checks. First of all, if I apply this formula to the generalized free field, it recovers the correct double chase coefficients, which were known before. A more interesting statement is that if I take, this asymptotic behavior, if I for a moment pretend that stress tensor coefficients are exactly given by this asymptotic formula, then I can perform this sum exactly again and compute the two-point function. And the two-point function, if I look at it in the complex tau plane, satisfies, well, it's KMS invariant with this spectrum, but it's actually free of singularities in this strip from 0 to beta. So this, and then it's extended by periodicity to the rest of the complex plane. So somehow this Borel resummation magically kills off the singularity. And it's also bounded as you go to imaginary time, which is also a necessary condition for thermal two-point functions. And actually, if I take these three properties, they seem to be defining a unique function. So we didn't really try to prove this, but it seems to be true. So it's somehow interesting that this seemingly unique function is indeed recovered by this solution, Borel resummed solution. Okay, so now we want to go a step further and go beyond this asymptotic regime, thanks, and input the exact stress tensor coefficients. So we don't have infinitely many of them. We can only compute finitely many of them, so we need to use also some numerics. And I won't go into the details, but essentially that means that you need to do both Borel resummation, which is slightly different from the one that I showed, and some Padé approximation of the Borel variable. So you do Borel, then you do Padé, and then you invert. And this gives you an approximation for the double trace coefficient. And what controls this approximation is this capital N, how many stress tensors I kept. So what I want to do is increase this capital N and see if this procedure converges and what are the numbers. So this is the picture for some examples of double trace coefficients. So you see this converges pretty well. For the first 8 operators, this table shows the result, and the number of digits that is kept here is the number of stable digits under increasing n further. So I should say this n is around 300 for this example. This is how many stress tensor coefficients we can compute. Another check of the resulting two-point function is this behavior along the imaginary tau direction, that it should be bounded by the value on the real axis, and this is also satisfied. Finally, you can try to compare. I said that the partial differential equation in the bulk is not really possible to solve it very precisely, but you can kind of solve it and then substitute these Padé-Borel values for all the thermal coefficient except for one. And then this gives you an estimate for let's say I pick this coefficient. this gives me, as this black estimate is kind of what I get from the partial differential equation if I substitute for all the other double traces. And you see, and the green one is the actual pas de Borel for the same coefficient. So here there are comparisons of these numbers. So you see that these numbers are always fairly close. And here I just put the GFF, generalized free field, to show that they're both well separated from the generalized free field, so that it's somehow not every two-point function looks the same. In this case, also this asymptotic model works pretty well, but that does depend. So this is for external dimension 3/2. This depends a little bit on the external dimension. So we have similar results for 5/2. Okay, so let me summarize. We proposed this method, which is essentially just based on simple linear algebra, how to solve KMS conditions, KMS sum rules, but it does importantly require this resummation in order to converge. We applied it to these holographic CFTs to learn about the double trace data and in turn the full two-point function. And it passes several consistency checks. There are some obvious generalizations, like you can repeat this where the points are separated also in space. I think this should be relatively easily done, and then you would be probing thermal coefficients distinguished by spin. Or you can go to finite S1 times SD minus 1. Then you are really probing the actual OP coefficients of the flat space theory, so this is also very interesting. In even dimensions, probably this can be carried out in a very similar way because the stress tensor sector is known in all even dimensions, or the method to compute these coefficients is known. There are other interesting directions, like from this knowledge, we can now start looking into the result, into this two-point function that we got and its properties, compute maybe Lanczos coefficients, quasi-normal modes. Importantly, I think also some of this is very general. You don't really need to have a holographic CFT. Well, KMS condition is of course true in every CFT. It's a question where you have this separation between different towers of operators such that one fixes the other. So this is an interesting question, I think. And a model that we are looking into is large N1 model, which has sort of a similar structure. Finally, it would be also very interesting to go beyond large N, or to have some field theoretic computation of these thermal coefficients, which I'm not familiar with any such calculations, but yes, it would definitely be interesting to have those. Thank you.
Well, we have time for a couple of questions.
Why do you have only phi and TT in the OPE? Why there is no phi TT? Well, phi T.
They are suppressed at large N.
Phi T?
Phi T, yes, yes.
Why would they be suppressed?
By powers of 1 over N. I don't know exactly by what powers, but they are suppressed.
So what would be the action you consider? I mean, gravity action.
So no, we don't. I mean, it's just the counting of powers. Like this, you can think of this thermal two-point function as a 4-point function of 2 heavy operators and 2 light operators. And then if you write diagrams, so let's say I have these 4 operators now, 2 of which are light, 2 of which are heavy. and then you have graviton exchanges or you have scalar exchanges. And then if you have more than a single graviton, for example, if you have graviton loops, you can do, when you do the counting, they all contribute at the same order. So this is why you have these multi-stress tensors. But I mean, I don't know. We can do the counting after. I don't think it's very, very deep, the statement.
But when you do the computation, you just use the gravity background, right? The black hole. Well, it's thermal ADS-CFT background, ADS background. So in this background, what action for the scalar field would you consider?
In this yeah, this is just minimally coupled scalar. Yes.
Just free action, or not?
Yeah. This is just free. And this will depend. Of course, you can do a different coupling, and then the stress tensor sector will change, and then the double chase sector will correspondingly change.
Well, thank you, Ilya, for the talk. Yeah, I was interested in the large N1 model, like what are the...
Yeah, so the structure looks similar because there, when you introduce the Hubbard-Stratonovich field, then you have double traces made of phi, and then you have the powers of the sigma field. So you have kind of two towers, and it looks then on a technical level very similar to what I was describing here.
Yeah, thanks for a nice talk. For the generalization, for example, finite separation, do you expect to have the same upper triangular Toeplitz matrix form that allowed you to have this nice solution? Or do you have any idea?
It's a good question. Actually, we are now solving it in a slightly different way. So we might, yeah, I don't know. I think we have now a slight reformulation that works at finite distance as well. So maybe we will, yeah, do it in a slightly different way.
Thanks.
Thank you very much. So first, I would like to thank the organizers for allowing me to speak for the first time in a Eurostrings conference. So I will be talking about the paper I released last year with Elias Kiritsis and Francesco Nitti, and Elias is here somewhere in the audience. And this paper was about confining theories on spacetimes with positive curvature. You might have noticed that in nature, quarks do not appear as free particles, but instead they are confined in bound states known as baryons, which are made of free quarks, for example, protons and neutrons. Of course, there are also other confined stable bound states, but these are the ones we see in everyday life. And this fact that quarks at low energies do not propagate as free particles is known as confinement. And it's made possible by the fact that quantum chromodynamics is a strongly coupled theory at low energies. In addition, QCD exhibits another interesting feature, is that at high energies, it becomes a free theory. And this implies that there exists a deconfinement transition. So what does this mean? So let's say we have a gas of baryons and we heat it up. When we heat it up, we put energy into the system, taking the theory to its high energy regime, and it will break the baryons apart. So there will be a thermal phase transition from a confined phase of a baryon gas to a deconfined phase of quark-gluon plasma, where the quarks and gluons are freely propagating particles. Now, this deconfinement transition can also be driven by quantum fluctuations instead of thermal fluctuations. And in this case, it's a quantum phase transition which happens at 0 temperature as a function of some other parameter instead of the temperature. And one way to do this is to put the theory in a box. So if you imagine putting the baryon gas in a small box, only small wavelengths will fit inside, corresponding to high frequencies and high energies. So this is a way to probe the high energy sector of the theory. So what will happen is that if you start with a big box and then compress the gas at some small volume, the gas will deconfine into a quark-gluon plasma. And this is a quantum phase transition now driven by quantum effects. And this is the topic of this talk. We will study deconfinement transitions at finite volume at 0 temperature. And the way we obtain finite volume is by putting the theory on a spatially compact de Sitter space. And in addition, in this talk, we will only work in Euclidean signature. So the de Sitter space will actually be a Euclidean sphere with some radius alpha, which controls the size of the box. And furthermore, we will focus on strongly coupled large N-gauge theories so that we can use the holographic duality as a tool to study these transitions. And this means that we don't have any quarks in the theory, and by confinement, I mean these glue ball bound states, which are kind of confined bound states made of gluons only. So we assume that the quantum field theory we consider arises from an RG flows from some strongly coupled fixed point UV conformal field theory. So near this fixed point, the action of the QFT takes this form where we have the action of the CFT plus some relevant deformation with a relevant scalar operator whose scaling dimension is smaller than d. And here lambda is the relevant coupling, and zeta is the metric of the background sphere. And so given these two length scales that we have available, we can form a single dimensional curvature parameter, R. So here we have alpha, which is the radius of the background sphere, and then this combination here is the length scale associated with the relevant coupling. And now at large curvatures, meaning that the sphere is very tiny, the radius is very small, this probes the high energy sector of the theory, like I said, that only high frequencies fit inside the box. And small curvatures, meaning that the sphere is very large and looks approximately flat, this is the low energy sector of the theory. So basically this dimensionless curvature can be used as a parameter to parameterize the energy scale, and this point of view was used in holography in these two papers from a few years ago. And a lot of focus on, in general, in quantum field theories in positively curved spacetimes has been put by these authors, which is an incomplete list in the recent years. So kind of the new thing of this work is that in the infrared, we assume that the theory is confining instead of, for example, flowing to a infrared fixed point. And what I mean by confining is that it exhibits confinement in flat space. And the theory is set to exhibit confinement in flat space if the Wilson loop has an area law. So this corresponds to a quark-antiquark potential glowing linearly at large distances. And we cannot apply the Wilson loop directly as a criterion on a compact space because there's no space to take the Wilson loop to be arbitrarily large. All right, so here's the outline of the talk. So first I will introduce the holographic model that we use to study these deconfinement transitions. I will classify the gravitational solutions of this model and then finally draw the phase diagram. So we consider a bottom-up model for a confining quantum field theory in d dimensions, and this means that the bulk theory will be d+1 dimensional. And we will consider a Euclidean Einstein scalar theory with this action. So it's Einstein gravity minimally coupled to a scalar field phi with some potential v of phi. And this scalar field phi is dual to this relevant scalar operator, which drives the RG flow. And we assume that its scaling dimension is larger than d/2 to be in the standard quantization in the bulk. And so what we will do is we will look for back-reacted domain wall solutions of this theory, where the domain wall slices are spherical. So more precisely, the metric takes this form, where u is the holographic radial coordinate, And then we have some scale factor A, which is the only degree of freedom of the metric we consider. And then phi also has this simple dependence on the holographic radial coordinate. And now we have to choose some potential, because this is a bottom-up model. So first we will choose that at phi equals 0, there's a maximum with a negative cosmological constant. And around this maximum, there's a mass term for the phi field whose mass is fixed in terms of the dimension of the dual operator in the standard way. So this means that this describes the UV fixed point. And so for the holographic radial coordinate, this is reached when it goes to -infinity, where the scalar field goes to 0 with the non-normalizable and normalizable mode in the usual way. And the metric in this u goes to -infinity is an asymptotically locally ADS metric, where the conformal boundary is now this sphere on which the dual theory is living on. And so that was the phi equals 0 behavior. And at large phi, we assume that the potential has exponentially diverging asymptotics. So basically, the potential starts at some maximum and then diverges to -infinity exponentially. The exponent is positive and this coefficient is negative, so that it indeed goes to -infinity. And what this does is that there will exist kind of a soft wall. So if you were to solve for the metric given this potential, you would find that the scale factor shrinks to 0 size at some finite value of the holographic radial coordinate, and the space ends. So the Euclidean solution ends there. And why do we consider exponential asymptotics? Well, the reason is that this will make the dual quantum field theory confining. In particular, it was shown based on these two papers that if the exponent of the potential is larger than this BC and smaller than this value, then the theory exhibits confinement in flat space. So more precisely is that if you look for domain-wall solutions with flat slices in this Einstein scalar theory, and you compute the holographic Wilson loop given a solution, then you find that it exhibits an area law in this case. So this Wilson loop can be computed as some Nambu-Goto action of a string wall sheet. And this kind of potentials with these exponents also arise naturally from dimensional reduction of pure Einstein gravity. So if you consider d plus n plus one-dimensional domain-wall geometries with SD times Sn slices and dimensionally reduce over this Sn, what you get is Einstein scalar theory with the potential, exponential potential, with exponent given by this expression. And for dimensions greater than 1, you find that this exponent here is exactly in this confining regime. And in this context, also this upper bound for the exponent is known as the Kupser bound. So basically only these exponents have an uplift to pure Einstein gravity. Okay, now I will classify the gravitational solutions of Einstein scalar theory here. So there are 3 distinct types, which are type 1, type 2, and type 3. And they're classified how the scalar field behaves at the endpoint of the geometry, where the spheres shrink to 0 size. For type 3, the scalar field is finite at the endpoint, while for type 1 and type 2, the scalar field diverges logarithmically to infinity at the endpoint. So this is kind of a schematic of what happens. So for type 3, there's a regular infrared endpoint for a finite scalar field, while for type 1 and type 2, basically the scalar field runs to infinity into a singularity. And in addition, this type 3 and type 2 each come with one integration constant. So they form kind of one parameter families of solutions. And then this type 1 solution is a unique solution that sits in between the type 2 and type 3 solutions. So the type 1 can be reached from either side. And this has a nice picture from the uplifted point of view, where the type 3 solutions uplift to this kind of geometry, where the SD corresponding to, which is the sphere where the quantum field theory is living on, shrinks to 0 size in the bulk, while the type 2 has the internal sphere shrinking to 0 size, and type 1 has both spheres shrinking to 0 size at the same time. So here we see that even though, for example, type 2 has a divergent scalar field in the downstairs theory, it still uplifts to regular pure geometry in higher dimensions, and it's regular from the higher dimensional point of view. So now I will talk about the phases. So the quantity of interest to us is the renormalized Euclidean path integral defined by this expression, and it's only a function of this dimensionless curvature parameter, which is the only dimensionless quantity available. And now, in our case, we are looking at large N strongly coupled theories, and this means that the holographic duality relates this path integral to the Euclidean gravitational on-shell action. So what you have is a relation of this type, where this logarithm of z we call the free energy. And what one has to do is one has to solve the equation of motion in the bulk with such that they give the correct dimensionless curvature on the conformal boundary, and then search over all possible bulk solutions, compute their on-shell actions, and pick the solution which has the smallest on-shell action to compute the free energy. And this means that there will be competition between solutions, meaning that there might be kinks in this free energy, and they would correspond to phase transitions as a function of R, quantum phase transitions. So in our case, we have this type 1, type 2, and type 3 solutions, and the type 2 and type 3 have one integration constant, and this integration constant is fixed by giving this R on the conformal boundary as a boundary condition. And what happens is that either there exists only a type 2 solution for a given value of R, or only type 3, or both, and then they compete, and one has to find which has the smaller on-shell action. And generically, in our case, what happens is that for small values of R, only type 2 solution exists, while for large values, only type 3, and then in the middle, where you have the type 1 solution corresponds to some fixed value of R, there's some overlap regime. But this already means that because only one of the solution exists in different values of R, there must be a transition from type 2 to type 3 as you increase R. And this is the holographic realization of the deconfinement transition as you decrease the size of the box of the dual quantum field theory. And this also shows that the type 2 solution corresponds to the confined phase of the theory, the large box, while type 3 is a deconfined phase corresponding to a small box. And this one can also confirm by studying the spectrum of fluctuations around these solutions, and the fluctuations around the type 2 solution are discrete, describing the confined glue ball bound states, while for type 3 it's a continuous spectrum. Right, so what we showed is that analytically that there exists a special value BE, which we call the Efimov bound for this exponent B, which is above the confinement bound. And it plays an important role in the sense that it controls the nature of this phase transition. So we showed analytically that if the exponent of the potential is above the Efimov bound, then the deconfinement transition between type 2 and type 3 solutions is always first order, meaning that the derivative of the free energy is discontinuous at the transition point. While if you go below the Efimov bound, then the transition can also be higher order. So the way we looked at this was we studied the vacuum expectation value of the dual operator as a function of R. So R is here on the horizontal axis and the wave is on the vertical axis. This dot here in the middle is the type 1 solution, and this red curve is type 3 and blue is type 2 solution. So what you can see here is that above the Efimov bond, there is kind of a spiral around this type 1 solution, meaning that the wave is a multivalued function of the source or of this dimensionless curvature, meaning that there will be a first order phase transition from one spiral arm to the next. This actually has kind of approximate discrete scaling, which is known as Efimov behavior. But now, below the Efimov bound, there's two possibilities. So the first one is that the wave is still a multivalued function of R, and there will be a first order phase transition. But the difference here to this first case is that there's no spiral. But the second possibility is that the wave is a single valued function of R, and in this case the transition will be second or higher order, and we will be able to show that it's never infinite order, so cannot be a smooth transition. So here's a schematic again. So if the type 2 and type 3 solutions overlap as a function of R, then the transition will be first order, while if they don't overlap, then it's going to be second or higher order transition. And we studied this in a concrete numerical example. So we took a potential given by this expression here. This has the property that at phi equals 0, it gives you a maximum, and then at large phi, it diverges to minus infinity exponentially. What we did is we solved the equation of motion of Einstein's scalar theory numerically and computed the on-shell actions and the corresponding free energies numerically as a function of R. And we did this in 4 dimensions for the dual field theory. And here's a plot. So this is the free energy as a function of the dimensionless curvature of the dual field theory. So here on the horizontal axis is R and vertical axis is the free energy. And this is below, this is above the Efimov bound for some fixed value of B for the exponent of the potential. So what we find, or what we see here is that the type 2 solution exists for small values of R, as I explained, and the type 3 for large values, and then there's some overlap region. And if we zoom in on this region, we see that there's this classic swallowtail structure and a first order phase transition happening at this dashed line where there's a kink in the free energy corresponding to this first order transition. So indeed, this confirms numerically the analytical expectation. And we also see that the type 1 solution sits here, and it's always thermodynamically not favored compared to this type 2 and type 3 solutions. Then we also consider the value below the Efimov bound in this case. Now the plot looks very different as expected. So the type 2 solution is again here for small values of R, for small curvatures, and for large curvatures we have the type 3 solution. And then if we zoom in here where the type 1 solution sits, we get this plot. And now you see that basically the free energy is continuous. So the derivative looks to be continuous, so the transition is at least second order. There's some overlap region here, but this is a numerical artifact due to numerical noise. And what should happen exactly is that there's a type 1 solution sitting here, and then the type 2 branch ends exactly at the type 1 solution, and then the type 3 branch continues. And the transition happens across the type 1 solution. And according to numerics, we also find that it's a second order and not a higher order transition. So the second derivative of the free energy is discontinuous. So to conclude, we demonstrated this expectation that a deconfinement transition can be induced by curvature. In this case, we used holographic to show it. And there's a transition from this type 2 solution to a type 3 solution as you increase R. And then we also showed that this exponent of the potential for large field values plays an important role in determining the nature of this transition. Above the Efimov bound, it's first order, and below it's first or higher order, and in the numerical example, it was second order. Thank you for your attention.
A very elementary question. So you said that the scalar potential diverges to minus infinity exponentially. So why is that not a problem? Because your scalar Hamiltonian would then be unbounded from below?
Well, at least if you imagine uplifting this potential to higher dimensions, it will turn out to be negative, and the coefficient, so this V infinity, so the coefficient of the potential is minus the curvature of the internal sphere. So it will, so only negative values have an uplift, basically. So from that perspective, it's natural. And also, I guess, the coefficient of the potential interaction was negative for the scalar field. So maybe that also...
No, but yeah, I mean, it's always minus V in the Lagrangian, but in the Hamiltonian, obviously, it would have a plus V, and if the Hamiltonian is unbounded from below, you would have, at least at the quantum level, that's...
Well, this is the Euclidean action, so this should be already the Hamiltonian.
I see, okay, thanks.
Yeah, here. I'm vaguely aware of the like similar story in ADS. So you put a theory in ADS and you also use the radius to probe confinement. And there they have, I think, an interpretation of what happens also in terms of the corresponding boundary theory. So it's a non-local. So they don't turn on gravity, but on the, you still have a CFT on the boundary, right? Mm-hmm. And there, I think there is a conjecture that confine the transition is associated with the appearance of a relevant deformation on the boundary or something like that. I don't know if like. So how does do the two approaches compare, and can you, from your approach, extract more general lessons for other confining theories?
So I don't know much about this story on negatively curved spaces, but yes, you can generalize this setup to accommodate a negatively curved conform boundary, and then you can study what happens, and that's what Elias has done in a more recent paper as well. So you can look into that if you're interested.
next speaker is Pat Kassler. He will be talking about the general Cartan geometry of alpha prime correction.
Yes, thank you very much for the kind introductions. Thank you for the opportunity for me to be here to tell you something today about higher derivative corrections. And I know I'm standing between you and your nice dinner, so I will try to make it as relaxing as I can do. Okay. And I'm very happy that actually Lorenz told you already how hard it is to calculate string amplitudes, so I don't have to press on this point very much. And here, you know, what I even want just to do is I want to calculate tree-level amplitudes, so Veneziano amplitude. And then you have seen already on his talk this nice expression here with a lot of gamma functions. And in principle, we can expand these gamma functions in terms of alpha prime, so which just describes the length of the string. So this is very well known. And you also know that we usually not use string amplitudes directly because they are so complicated, but that we rather use an low energy effective field theory. So that means we match these string amplitudes with some amplitudes in our supergravity theory. So, and what we are doing there in detail is actually first we are identifying the relevant degrees of freedom, so which here is just the metric, the B field and the dilaton, so the NS-NS sector to keep it as simple as possible. And then, you know, we also look at the symmetries. So here we have diffeomorphisms, of course, because we have a supergravity, and we also have abelian gauge transformations for our B field. And now in the next step, we just write down and for our action all the terms which are allowed by symmetry. So we have this very well-known building blocks and we just combine them in all possible orders. And in principle, we get the blueprint for our low energy effective action. Of course, you know that you could write down an infinite number of terms, so we have to find some parameter to expand in, and this is usually alpha prime, which just counts the derivatives. So this is, of course, what you all know, and in principle, after we have now matched with our string amplitudes, we get here our coefficients. But of course, you also know that there are certain problems in this procedure. And the first thing is that this number of terms which we can write down really explodes. So for example, when we would like to go to alpha prime to the power of 3, we had already 872 terms. And we would have to calculate a lot of amplitudes, which makes it actually not feasible to really go much higher. And then the next thing, of course, is connected to what we already heard in Lorenz's talk, so that there are also loop corrections, which we also would have to take into account. And at this point, you know, we get this whole plane here of corrections to supergravity. And normally, we really just work in this very, very small corner. So at the leading order in GS and in alpha prime. And of course, we have seen that there are some nice techniques using holography, for example, to explore these parts here of the diagram, or we could use supersymmetry, which protects some states to go in the middle here. But in principle, we do not know what happens there. And so this brings me to what I actually want to talk about today. I want to give a proposal of how we can actually get in here and how we can learn more about these corrections. And so the idea, what this all is based on, is actually we go back to the effective field theory. And of course, we cannot do very much with the degrees of freedom. But what we can do is we can look more at the symmetries we have. And so, for example, you all know that we also have fermionic symmetries, supersymmetries, for example. But it's also well known that when we have a lot of supersymmetry, it's actually very hard to deal with explicit supersymmetry. So that's why people were also exploring other routes, for example, hidden symmetries, which are also a very nice thing and very constraining. But of course, recently there were some no-go theorems for certain hidden symmetries that they will not be able to capture all higher derivative corrections. And so that's why today I want to propose an alternative route, which is more along the line of spontaneously broken symmetries. And of course, you know that spontaneously broken symmetries have a very, very successful history in physics. And in principle, there is a very nice recipe you can follow. So you can start actually with what is called the coset construction, where you have a group G of your full symmetry, and then you keep just a subgroup, so the residual symmetry H. And then by choosing your field based on a coset representative, you can actually write down again a candidate for a Lagrangian, and you can match it with amplitudes again, and you will get a low energy effective action. So this brings me now to my proposal, actually. So I want to propose to you that higher derivative corrections, and in particular alpha prime corrections in supergravity, they might be governed by some infinite dimensional symmetry group, which I now just call G Poincare infinity. And what I want to do for the rest of this talk is I want to show you what is this group and how does it work. So that means this brings me to the two natural questions in this context. What is this group? And so the guiding principle here will be that, of course, to get a larger group, we have to add something to our theory, but we will add it in such a way that we don't add any new unphysical degrees of freedom. And the second question is, of course, how do we use this extended group to get, for example, an action or the equations of motion? And you will actually see that this will be done by also a coset construction. And this coset construction will be done by generalized Cartan geometry. So that means the first point, we will use a BV formalism, because so this is the way how we figure out physical degrees of freedom. And the second thing, as I already was mentioning, is done by Cartan geometry. And we will put both together, and then we have a recipe for finding out these higher derivative corrections. Okay, so let me give you an example, because this is very, very abstract. Let's do something which we all know, and let's count degrees of freedom in linearized gravity. So this is one of the simple settings we can take. And so we start with a frame field here, so which actually will have just the small fluctuations around the identity. And then, you know, in gravity, of course, we have symmetries, we have diffeomorphisms here, and we also have Lorentz transformations because we just have a frame. And so at the linearized level, they affect the frame exactly this way here. So, and to keep track of all these kind of things, we put this in a little diagram. So we have our diffeomorphism parameter here, and we have our Lorentz parameter here, and they all interact with the frames through this linear maps here, the exterior derivative, and this map here, which I will call tau. Then we can do the same for the spin connection, which of course does not transform covariantly, but it's d, the Lorentz parameter. So we also put it in this nice diagram, and we have here again the exterior derivative. And so we go on, you know, we can write down the torsion, we look up the equations and linearize them. And again, we find that it depends on the frame and on the spin connection. And you see, so putting in the curvature, we actually get a nice diagram, and we can go on. We would get Bianchi identities here for the torsion and for the curvature and so on and so forth. So the nice thing about this thing is that it's actually a bicomplex, and what we do here, so this is a little bit technical, we also have to expand it with a Weil tensor, and I will explain in a second why. But you see, the most important part is that we have two maps, so we have D's going along this side here, and we have taus going diagonally, and then when we square the respective maps, we get 0. So that means d squared will give 0 as an exterior derivative, and the same for tau, for example, along this route here. And then eventually we can also go this route or this route, and it will give the same result. So this is what this identity here tells us. And then, you know, of course, I was promising you to find the degrees of freedom in linearized gravity. So how do I do this? I, of course, use my new gadget, this complex here. And in particularly, we will start always going diagonal here. So we will start at this point. And what we are doing is actually we are calculating the cohomology. So that means we are looking at this line and writing down here a chain complex. And you see we have here our Lorentz parameter, and here we have our frame. And the Lorentz parameter is, of course, antisymmetric in these two indices. So we just put two boxes above each other, and the frame can be in principle everything. So this is box times box, which of course decomposes into a antisymmetric and in the symmetric part. But you see this antisymmetric part is killed by the Lorentz parameter, and so that's why we only keep the symmetric part. But of course, you all know that gravity has just a metric, and the metric is a symmetric tensor. So this is exactly why we have Lorentz transformations, to remove this unphysical degrees of freedom from the frame. So when we do this again, so we will find that the cohomology here is trivial, and this is very good because we can fix the spin connection completely in terms of the torsion. And then we can do it again and calculating carefully the Bianchi identities and taking into account the Weil tensor, we get exactly the Einstein tensor here, which gives rise to the equations of motion for our metric. And then doing again this cohomology, we will find exactly the Bianchi identity, the contracted Bianchi identity, which we need. So that means going along this line here in linearized gravity, we really see completely what the theory is doing. So we are seeing gauge transformations here, diffeomorphisms, we are seeing degrees of freedom here. And then what we are doing is we are doing this trivial cohomology. We use it to fix the spin connection in terms of a derivative of the frame. And then we get the curvature or the equations of motion as another derivative of the frame. And finally, we get Bianchi identities. So this is how it works. So this is how we can identify degrees of freedom for linearized gravity. But of course, you might argue that linearized gravity is very boring. And we would like to rather do the full thing, full nonlinear gravity. And so there we can now use Cartan geometry. And I want to quickly show you how this works. The basic idea is actually to compress this chain complex, which we have just in one line, so to unify it. And so what we are doing is we are looking first here at our diffeomorphism parameter and our Lorentz parameter, and we can actually unify them into a Lie algebra valued element, where we just take translation generators, pairing them with the diffeomorphism parameter, and Lorentz transformations, of course, with the Lorentz parameter. And so that's why we get one unified object here. And we do the same here for the frame and for the spin connection here. Again, translations and Lorentz transformations. And the same can be done for the torsion, the curvature, and also for all Bianchi identities. And so this way we take all what we have here just in one single line. And for the moment, we don't care really very much about the Weil tensor. When you are interested in this, I can tell you later on more about it. But so then the last thing we have to do is we also have to unify these maps, D and tau. And so what we can do is actually we can write them in terms of what people call a Cartan connection. And this is really like your normal gauge connection in a gauge theory, D plus, and then you have a connection one form here, which you wedge with. And this Cartan connection actually includes the frame and also the spin connection. And now the nice thing is we can really use the full frame here, the full nonlinear frame, and we will still get this nice complex which we started with. So this is what we are doing, and there is now a very nice interpretation here, because you see that we started with Poincare, but then we were eliminating the Lorentz transformation. So that means we are working on the coset Poincare mod out Lorentz transformation. And of course, you know that this is just flat Minkowski space, which we use here as a tangent space on this point. So what we are doing is we are doing a coset construction on every point of the manifold. And this is exactly what Cartan geometry is doing. So now I have shown you how you get Poincare in gravity, but of course this is something what you know, and I promised you something else. I promised you Poincare infinity, right, which is much more fancy. So how do you get this one? And to get this one, the only thing you really have to keep in mind is that the string is an extended object. So it will not couple like an electron, for example, to a one-form field, but it will couple to a two-form, the B field. And then, of course, this two-form has a three-form field strength. So why is this so important? This is so important because when we look at transformations of this two-form, so we see that it has a D of a one-form and it has diffeomorphisms. But so because this is a one form and not a zero form, we can take this one form as D of a scalar, And so we have a transformation which will still not change the B field. So this is the notion of a trivial gauge transformation or gauge-for-gauge transformation. And this thing we have to take into account when we now try to write down the same complex which we wrote for normal gravity for the string. And so we not just start with the parameter for the gauge transformation, but we also have this gauge-for-gauge here. And then in principle, you know, we can now try to write down all these other spaces by now taking into account that we not just have one box here for diffeomorphisms, but also one additional box for B-field gauge transformations, because so these are one-form gauge transformations. And then, of course, we need to know all these spaces. But here again, Cartan geometry helps us. And it's, of course, not normal Cartan geometry, because now we also geometrize this gauge transformations for the B field. So that means we have generalized Cartan geometry. And at the moment, please just take generalized Cartan geometry as a black box. And the only thing what it's doing is that I know these representations or these vector spaces here, and it will tell me what I have to put here. So, and I will explain you in a second a little bit more how this works, but for the moment, this is all we need to know. So, and what we are doing now is, so we are just going along this line. And here we have to, again, put our degrees of freedom. And so our physical degrees of freedom are just the metric, the B field, and then the dilaton, so the one from the second slide. And then when we do the cohomology again, we see that we not just get one Lorentz transformation, but we get actually also a second Lorentz transformation. So this is what's called double Lorentz transformation. And this is, of course, a standard feature of the closed string, right? Because we have a left-moving and a right-moving sector. So this is still fine. The really interesting thing, which is different from normal gravity, happens now. Because when we now look at the torsion here, we will find that it's not sufficient to fix the spin connection on its own. So this is a very well-known problem, so that the spin connection has more components than can be fixed by the torsion. And the solution, so I would like to propose, is actually to use a new symmetry, some kind of a Stückelberg-like symmetry, which actually gauges these components which you cannot fix. And so you get this additional gauge symmetry, and then you can complete your cohomology, and actually you can get a trivial cohomology here. So, and then you go further on, you know, so you now get some additional spin connection for this new symmetry here, and you also get a spin connection here for your gauge-for-gauge symmetry. So this is special and generalized Cartan, but in principle, you can go on and do the same cohomology. Here we want to just keep our standard equations of motion, and when we do this again, we get some additional representations, and these will actually furnish Poincare infinity. So here you see this part here, and this part would be normal Poincare, translations, and Lorentz rotations, and now you get two copies of it, and it goes on for infinity. So this is the idea here, and for a second I just have to tell you what is this mysterious generalized Cartan geometry, and I don't have very much time, and we want to go to the dinner, so that's why I just tell you this always arises when you have gauge-for-gauge symmetries like this one here, and then you also have to add additional connections for this gauge-for-gauge series. So the thing here I call rho, and then they come with curvatures and so on and so on and so forth. And for the experts among you, so this actually follows what people call the tensor hierarchy. And then what you get is, so you get this kind of nice new model space. So now in generalized Cartan geometry, a coset is actually G mod out H twiddle. So you get a double coset, and the double coset will actually describe your generalized tangent space, which is normal tangent space for diffeomorphisms, and then you have a cotangent space for B-field gauge transformations. And what we have achieved by this cohomology discussion, we have just fixed this part here. So for normal Cartan geometry, this would be all, but now we also have here another Lie group, H, and this one is not fixed yet. But what we can do is we can actually use the fact that this together has to form a Lie group on its own. So that means these generators here are tightly constrained, and we can actually fix them completely when we just define a bilinear form on them, which can be used to reflect what we already know from here to here. So let me quickly show how you get corrections from these prescriptions, how you get higher derivative corrections. So what we are doing is actually we first take into account that we now know that these things are in the Lie algebra, and this new Lie algebra we have seen for H. So we can just write them as Lie algebra valued, and the diagram looks already a little bit nicer. And then what we are doing is we are doing this zigzagging procedure. So that means here we have our frame, and then we have our trivial cohomology, so we can express our spin connection in terms of one derivative of our frame. And then we can go on again. So, and we now can express these higher connections with two derivatives of the frame. And this goes on and on and on here. And you see when you go down here, the number of derivative grows. So that means this will automatically give you alpha prime corrections here, and of course an infinite number of them. And then the question is, how do these alpha prime corrections land up here? And this is actually, when you look at the linearized level, you will not see it, but at the nonlinear level, you will see that you have a commutator between two of these connections. And then you just have to remember what this Lie algebra H is. So when this kappa here, which controls this Lie algebra, vanishes, it is just a graded Lie algebra. So that means to land here, we have to have a 0 here and a 0 here. So that means we will don't have any alpha prime corrections, but when the kappa is non-zero, we will get a filtration. So, and all these higher correction terms will land in our equations of motion, and we get a tower, an infinite tower of higher derivative corrections. Okay, let me quickly now say how this relates to the literature. So the only thing which we now need to know is this kappa here, and we in principle can parameterize it now. We have to check which of these kappas are admissible. And we, for example, know very certainly that we have at least two different choices of this kappa, one for the left moving sector and one for the right moving sector. And we also have seen, so this is work in progress, but it's very likely that there are even some more, so some like C and D. And now we can check what this really means. So this will always give you different towers of higher derivative corrections. And the first one we have identified with the known results from the literature. So this actually gives rise to what people know as the generalized Birkhoff-Durot identification. And so far, this was just calculated to alpha prime square. But with our result, we can write down all order results. So we can really write down transformations to all orders here in alpha prime. And then these two new parameters here, they will give rise to a new tower, which starts at alpha prime to the cube. And this is exactly the one you need to capture the theta 3 transformations. So, and this is very nice because it circumvents a no-go theorem for this alpha prime to the power of 3 tower that you cannot obtain it just from a hidden symmetry. But of course, we not just need this hidden symmetry, we have an infinite dimensional symmetry. Okay, so let me finish. So what I want to just quickly recap. So I told you a little bit about field theories, symmetries, and geometry. What I did not tell you because I did not have time, so what I was doing now was only string-based, but the whole lot of technology we are using can actually also be done for membranes. And we have now a generalized Cartan geometry for membranes, where just here the full tensor hierarchy of the membranes arises, and we get more and more corrections. And so this is very interesting because we could probably even do GS corrections. I mean, this is what we are trying to do. And another nice aspect is that we can also have different realizations of these algebraic structures, and this will give rise to dualities in string theory. So there are a lot of possibilities. And here I just want to stop and thank you very much for your attention.
So you started saying something about string as matrix.
The scattering. Yeah.
Yes, and that encodes all information about this effective action, say bosonic string theory. So normally we are used to this idea that if there is some symmetry which is really relevant, not these cohomologies, not gauge ghost for ghosts, etc., physical symmetry, it should be encoded in this matrix.
Yes.
So do you have any suggestion?
Yes. This is a very good question. I mean, so what I was now doing is it was just the target space perspective, but when you would do it on the world sheet, so what I'm claiming is that the number of counter terms you can add to your action is very, very much restricted. And there is some symmetry which really restricts the amount of counter terms which you can write down. And to give you an example, so just very, very quickly, yeah, let me show it to you here. So here you see it. So at alpha prime to the power of 3, I was telling you, in principle, you can write down 872 counter terms, already mod out by field redefinitions. And what I'm telling you with this symmetry, you can actually just write down 4 counter terms. Exactly. What these constants are, I mean, the funny thing with these constants is you have a Z2 symmetry, left and right. So that means they will be fixed differently for bosonic, heterotic, and type 2. And then here you will find for this concept something proportional to zeta 3. So this you still have to calculate from the string scattering. I mean, it does not know about these values of the constants. It just tells you you have much, much less to calculate because there is an internal symmetry. Okay. Thank you. Thank you.
Thank you very much. Let's see if this works. Okay, great. So I would like to start by thanking the organizers for putting together this great event, and to all of you for coming, even this late. And okay, so I would like to also thank the organizers for giving me the opportunity to present our recent work. This is done in collaboration with Julian Kupka and Charles Strickland Constable, and it concerns these works. And so what I want to talk about is some new developments in the relatively old subject of n=1, d=10 supergravity. So there will be 2 topics that I want to talk about. One of them is a simplification that one can do in order to study the n=1, d=10 theory, including fermions to all orders. And the second one is how to build a BV formulation of this theory. So as far as we are aware, this is the first time that a BV formulation of a higher dimensional supergravity has been written down in a sort of background independent way. And so this is made possible by some very, very useful tools. So there will be 2 of them. First one is the so-called generalized geometry, which you can think of as simply as some sort of efficient repackaging of fields and action and symmetries in some sort of smaller amount of variables, in a way that where you don't introduce any extra fields, any auxiliary fields, and you don't remove anything. So it's really the same stuff, except it's like a more sort of concise language. And in particular, one of the advantages is that the Yang-Mills supermultiplets are included for free, including their coupling to the theory. And of course, it's fully geometric as well. And the second simplification, which seems to have gone sort of underappreciated in the literature, is this fact that you can, in fact, just do things directly. And the message I'm trying to convey is that you can just work with metric formulation directly. You don't need to introduce any field binds or Lorentz symmetry in order to tackle the coupling of fermions to gravity and all that. So you can just do things directly. There will be some interesting geometry behind this, of course, but as you will see. But yeah, and in particular, this considerably simplifies the structure, because now you don't have, when you don't have Lorentz symmetry, then you only have the diffeomorphisms, the B-field gauge transformations, the gauge transformations for the fields, and the local supersymmetry. And you will see that the algebra is very, very small, kind of. And this fortunately applies to supergravities in all directions, while this generalized geometry framework is specific to 10D, at least in the way I'm going to present. Okay, so that's the outline. Now, so what is this theory in question? You perhaps all have seen it. So, the only data that you need to specify in order to build this theory, because of the large amount of supersymmetry, is a Lie group or Lie algebra, at least locally. Globally, you can do some interesting patchings. But for local description, you only need to have a Lie algebra with an invariant pairing, and then you can construct the following theory, where the bosonic field content is the graviton, the B field, gauge field, a dilaton function, and the spinners, or the fermions, which are spinners, In particular, gravitino is a vector spinner, so it carries a vector index. Dilatino is simply a spinner, and gaugino is a spinner valued in the Lie algebra. And so the action for the theory looks like this. So perhaps you are most familiar with the beginning, which is the bosonic bit. And occasionally you might glimpse these quadratic fermionic terms. So this is this kind of red or purple, red color. And the thing you don't see at all, unless, okay, almost don't see at all, is this quartic fermionic terms. So as you see, like it goes quite beyond the bosonic bit. And the claim is that this is invariant under the following set of supersymmetry transformations, where again the red ones are highlighted, like these are the higher fermionic ones. And so this theory was constructed in these papers, essentially, in the 80s. But I want to point out the thing that if you look into those papers, then the formulation you will find is substantially longer. And the way I presented it here is kind of a result that we got from our work in generalized geometry, in that, for instance, we showed that it's possible to organize the theory in a way where, for instance, you only ever encounter gamma 3s, so gamma with 3 antisymmetrized indices in these higher terms, and you never have any contraction of gravitini with the gamma matrix indices. And it will be clear in a moment why that is the case. So yeah, so already the way the result that you can write this theory in terms of classical variables, of these things, like this, that's kind of a consequence of the generalized geometric treatment, and it's not at all obvious when you just start by reducing 11D theory. But the formulas I'm going to show you in a moment are much simpler, actually. In generalized geometry, these things significantly simplify. So what is this generalized geometry? So some sort of crash course. In fact, the only thing you will need to know is that the starting point is simply, you look at your theory, so supergravity, you look at its local symmetries, so you have diffeomorphisms, you have one-form gauge transformations for the B field, and you have some gauge transformations for the connection, for the gauge field. So you just put them together in this kind of formal sum in this new vector bundle over, let's say, R10. And you notice several features. For instance, there is an interesting bracket, inner product on this space where you can just pair T with T star, and you pair Lie algebra with itself using the invariant pairing. There is also a natural map that projects the stuff down just to the first component. And most importantly, there is a bracket which takes this form and which is capturing the symmetry algebra here. So that's one way to arrive at such an object. Notably, this bracket here satisfies the Jacobi identity, although that's kind of not obvious. Okay, so that thing, so having defined this, now you can start encoding the fields. So the claim is that the bosonic fields are easily encodable by taking simply these two objects. So we define a generalized metric to be a map from this bundle to itself, which squares to the identity. This is just a fancy way of saying that we are splitting the bundle into the plus minus one eigenbundles of G. So this is the same data as splitting of the bundle into 2 bits, which are orthogonal. So we will call them C plus and C minus. And so the way you encode most of the bosonic field content is simply that you draw this picture. So you have tangent bundle, you write the rest. So this is together, this plane represents E. And then if the dimensions were, if you restrict your attention to some specific subbundles of some specific rank, then you will see that the C plus looks something like this, and you can read off that this is a graph of some linear map from T to the rest. And if you look at it, then that's precisely metric plus B field plus A field. Right? So because the map from T to T star has a symmetric and antisymmetric part, that's G and B. Map to G is simply the connection. And so the only bosonic field that is missing is the dilaton. So the dilaton is simply encoded here as a half density. So H here is a line bundle of half densities on the manifold. That's going to be very important, sort of. Also, but this is not a new treatment. Like it's kind of this is the factor that appears in the string effective action anyway. So this is how you read off your usual functional treatment of the dilaton. Okay, so this is the bosonic fields. Now the fermions are actually not much harder. So if you assume that the signature is 9, the induced signature on the subbundle is 9,1, which is what you want for supergravity, and we define the Majorana-Weil spinor bundles for this subbundle C+, we call them S plus minus. Note that we will not use spinors for C minus, only spinors for C+, because this is type 1 theory. So having defined the subbundles, now you just proceed and you just declare that this is your fermionic content. So there is a generalization of the dilatino, where this capital Pi simply stands for parity shift. So this just means that the field is bosonic, fermionic. And you see that this the dilatino is a spinor of some chirality, but it also has a half density component. So it's not a function, it's a half density. That's kind of important because it turns out that this kind of eats a lot of nasty terms in the variations and in the action. So this is kind of like a field redefinition. You multiply it by the dilaton. But in any case, the more important one is the gravitino, which turns out to have, as you saw before, it has a spinor index of opposite chirality. It is a half density, but it's also a vector. But now the kind of the most crucial observation here, observed in the paper in these papers, was that the vector part of the gravitino is living in the C- bundle, while the spinors here were constructed for C+. Which means that, for instance, if you are going to write some bilinears of these things, then you are never allowed to contract the gamma matrix indices with the vector index on psi in generalized geometry. That's like just not possible. So this thing tells you that there is only a couple of things that you can write that respect the symmetry, and it turns out that those are precisely the terms that appear in supergravity. Okay, and just one last technical term. Without going into details, so in generalized geometry, there is a way to construct natural analogs of operators in Riemannian geometry. So you can construct scalar curvature, Dirac operators, etc., etc. And here I'm just adopting the convention that Latin and Greek indices stand for some frames in C+ and C-, respectively. Okay, now with all that, I can just tell you that this is the result. This is the action written in those variables. So the orange part goes back at least to the work of Siegel, anyway, let's say Siegel in '93. So that this is the entire bosonic part of type 1 supergravity. The fermionic part, in the lowest order, was known already in these papers and constructed also, the variations were also constructed. And so now what we did essentially is that we observed that there is only very small number of terms that you can write when you respect this kind of structure of the index structure, and it turns out that these are the only two terms that you can write, up to some coefficients. So we wrote those two terms, put some arbitrary coefficients, we put some arbitrary higher spinor variations here, put some arbitrary coefficients in front of those, and then we just checked by hand that for these numerical values, the action is actually invariant to all orders. And you can do the check by hand. It took quite a while, but it's actually written up in the paper. It's just a couple of pages calculation, which is also, maybe I'm wrong, but I think that's probably the first time that such a calculation was exhibited in a paper, like explicitly. So this kind of like a direct proof of supersymmetry without relying on any other arguments. But okay, you can go further. So you can study the symmetry algebra. So as we said before, this bundle E was already constructed in a way that it encoded all the bosonic local symmetries. So sections of these zetas, they are formal sums of diffeo or infinitesimal diffeos, one forms, and gauge transformations. And in generalized geometry, there is again a natural counterpart called generalized Lie derivative, which kind of encodes this action on all the fields that we saw before. There is, as was mentioned also before, the one-form gauge transformations are reducible, so strictly speaking, you have to include some ghost for ghost, but that's not terribly important. What's more important is the symmetry algebra. So this is actually a deceptively simple-looking result, behind which there is quite a long calculation done by Julian. So the result, so this is the symmetry algebra of supergravity. Once you exclude all the, if you do it directly in the metric formulation without any field binds or Lorentz transformations. So you have there, as expected, that two diffeos close into a diffeo. Diffeo and SUSY give you a SUSY, and the commutator of SUSYs, which is the most important and most interesting part, is given as you would expect, or as is expected in supergravity theory. There is, most importantly, there is a diffeomorphism term, which is constructed out of epsilon1, epsilon2 in this way. There is also supersymmetry, which is of higher order in fields, and which depends on the dilatino. So this is not unexpected. But what is kind of slightly unexpected is that this is all, and there is like really no need to include any. There is no Lorentz transformations actually appearing here, and in fact, even the part proportional to equations of motion can be written down. Which again, I'm not aware of a paper where this would be written down. I mean, maybe there was one, but definitely not in the old papers. But anyway, so the claim is that you can show that this is what's happening. This is the algebra. And okay, and then you can go further and you can ask a question that you in principle could have asked also on the previous slide. So you can ask, what is actually the meaning of these objects? Like, what is the geometrical meaning of these variations? Because spinners, the fermions are spinners, and spinners are defined with respect to an underlying metric. So they are sections of a spinor bundle constructed for a given metric. And when you are making a supersymmetric deformation of things, then you are also changing the metric, which means that this thing, which should stand for some infinitesimal difference of two objects, it cannot really be an infinitesimal difference because it's like the new spinner lives in a different space than the old spinner. So what is actually the meaning of this? And the meaning is kind of nice and geometric. The meaning, oops, oh, I see. This is what happened. Okay, so the meaning is that the field space really has the following bundle structure, that you should really look at it as having at the bottom the space of bosonic configurations, and the field space itself being the total space of this bundle, where the fibers are given by the fermionic configurations. And the kind of non-trivial claim, but not difficult to show, is that this bundle actually possesses a natural connection, which is, however, not flat. And this is the thing that allows you to identify nearby spinners for nearby generalized metrics. And so the picture to have in mind is this one. So this is the square is the whole, is total space. So this is the space of all fields. This diagonal red arrow, the delta, this is simply asymmetry, like let's say supersymmetry or generalized diffeomorphism. And right, so symmetries are vector fields on the field space, right? So this is the red arrow. But now using the connection, you can split this into a vertical and horizontal part using the connection, and that's precisely what the meaning of these symbols is in this kind of geometric metric approach. And as I said before, this connection has a curvature. So connection here, you see that it's represented by these blue lines. These are the horizontal spaces. And this connection is curved. It has a curvature. And this is kind of the technical reason why the Lorentz terms don't appear. I didn't present the calculation, but if you do the explicit calculation, then you will see that the way these Lorentz terms disappear is if you correctly take into account the curvature contribution when calculating this commutator. So, okay, I'm happy to discuss that later on. And maybe just to finish, let me show you the full BV supergravity. The BV formulation. So as we said, the physical fields are, well, these four guys. There is supersymmetry and generalized diffeomorphisms. That's all there is to symmetries. So we call them the ghosts, we call them E and Xi. And there is a ghost for ghost. And then there is antifields to each of them. So as usual in BV formalism. So I will denote them by star. And then this is the action. It might not look short, but it is very short. And if you know about BV theory, then the way you should read this is that the first two lines tell you what the classical theory was, what the theory you started with was. The next three lines simply encode the symmetry transformations. They tell you, like, for instance, if you're interested in how rho transform under supersymmetry, you should look up the rho star line, and you should look at the terms which contain the Susy ghost. So this is the supersymmetry transformation. So this is how we read it. Next line is simply the symmetry algebra, so this encodes these hard calculations about the commutators of supersymmetries and all that. The next line is, okay, this is less intuitive, this is the ghost for ghost contribution, but the important bit is the last line, which is quadratic in the antifields, and this is the thing that is responsible for non-closure of the algebra. And now the really non-trivial claim about this action that I wrote is that it satisfies the classical master equation, and that we, again, provide a full proof in the paper. It's now a bit longer than the preceding one, but you can do it. And hence, you now have a BV formulation of supergravity. And you can proceed and do things that you would like you can try to attempt some sort of quantization, or you can study anomalies, or you can study some other things. So now what can one do with this? So first, some conclusion. I guess there is, okay, perfect, thanks. So, okay, so as said before, so or as you saw before, this essentially completes the program of like reworking n equal 1 supergravity in generalized geometry. it is simple enough so that you can do a check supersymmetry by hand, in principle. And as far as I know, it's the first BV formulation in a background independent way of a higher dimensional supergravity. So up to now, I think there is like 4D and 3D, and now there is 10D. And it also confirms once again that generalized geometry kind of provides the right or the natural set of variables to use for the string massless sector. And in order to do this, just as a technical simplification, we use this direct metric approach where we avoided the Vielbein and the Lorentz transformations. And okay, just further interesting games that you can play with it are these two games, for instance. So once you formulate stuff in generalized geometry, then it turns out that there is some sort of special corners which you didn't see before. And one of them is, for instance, you can set this endomorphism G, you can set it to 1, in which case all the metric degrees of freedom and the associated spinners decouple. And the only thing that you're left with is this theory which has these kind of generalization of dilaton and dilatino. And it's topological and it's locally supersymmetric. And it's kind of like an interesting toy model. So we first figured out the BV formulation in that model, actually. Or you can take a second interesting limit. You can take your base manifold to be a point, and this turns out surprisingly to fit into the thing. And if you do it in a clever way, then you still keep the entire structure of supergravity, all the supersymmetry variations, the BV formula, like all the action, the long one from the preceding formula, but it's not finite dimensional. As is like the field space is finite dimensional. And so now the outlook, what you can do, one can try to do type 2, which is another place where generalized geometry is useful, or you can study some cool things such as the conjecture of Costello and Lee about the topological, or sorry, the topological should not be there, about twisting of supergravity and the way it links to the Kodaira-Spencer theory. So these are kind of interesting things for the future. So thank you. Okay.
Is it on? Oh. So you said that with this construction, it does satisfy the classical BV master equation.
Mm-hmm.
Any indication what you would expect if you would ask for it to satisfy the quantum BV master equation, and what you will have to like deform in the algebraic structure of the theory?
Mm-hmm. Okay, thank you. That's a very good question, a very natural one. So, so all sorts of, well, in quantizing the quantizing this theory would be kind of complicated. But what you can do, and what was done by Costello and Lee, is that you can perform a twisting of the theory. You can kind of move away slightly in this BV space from the locus that you normally study, and then the theory that you have becomes sort of much more simpler while still retaining many of the features of the original theory. And that one you can show, or they showed that you can perturbatively quantize in like a rigorous way even. And so, yeah, I mean, in building up the solution to quantum master equation, there is like all sorts of complications because this is like a, well, it's a very physical. I mean, it's a very big theory, so it has, you need to do it in a complicated perturbative way, and I don't know much about that, but you can look at the works of Costello and Lee where they do that in this twisted regime.